Okay, good morning and welcome to day 3 of the NSM workshop on HPC for CFD. So today we have Professor Ashok De from IIT Kanpur Department of Aerospace Engineering with us, and he's going to talk to us about finite volume methods with a focus on both incompressible and compressible flows. So I thank Professor De for taking valuable time out of his busy schedule and coming to IIT Bombay to deliver this talk. Professor De, over to you. Thank you.
No, it was off. I think, am I audible now? Okay, good. Yeah, Dr. Bikas, Dr. Ashish, Professor Somnath, and Professor Bharma. Okay, so let's begin with today's session. And obviously, you have to kind of tolerate me for both the sessions, morning and evening, or rather afternoon. Let's see how we can make it enjoyable. I mean, I can't guarantee that I can make you learn everything, but let's try to have some heads up on this particular topic that I'm going to talk about. And then morning half, I think you have a follow-up session on the incompressible part, which the TAs are going to conduct, so that you'll get to do some hands-on. And then the afternoon also you are going to do something on the compressible part. So that's the idea about this whole day's plan. So that's what obviously let's start with that before I get into the incompressible part. So let's think about something. I think you have been kind of going through different sessions or multiple sessions in last 2 days about CFDs and things like that. Probably I would say these are some of the questions that always ponder somebody, how we can make things more and more design oriented, or rather you think about that you can use CFD more for a design tool rather than, because the CFD has matured that much. So it has reached to a stage and it should be a tool for design purposes and it should complement to the industry. So that's the idea. So here I'll like to pose a problem like how you as an engineer or scientist can contribute there, and how rather if as a CFD community we can contribute. So obviously the way we try to contribute, so it should be a win-win situation. It's not a one-way traffic, it goes this way and the other way around. So CFD should be used for the design, at the same time the design problem should be posed to the CFD engineer so that they can provide some meaningful solution. Okay. Now, what are the possible solutions that you can have? So obviously the academia, which is more into your academic competencies, or rather you have that power to do something or think through something. So then you adapt to the interdisciplinary approach, and then you should have a capability. And let me put it this way, this all CFD and that we talk about, that I will term as computational aided engineering, because CAE. And why I say that CAE? Because this includes everything. So you talk about FEA, you talk about multi-body dynamics, you talk about optimization. These are to list something few, but it could be finite difference, it could be your spectrals, so other things. So what it means that it's a tool that you should use for your design purposes, and it should provide the information that to support the design as a thing. Okay, I mean, what CFD is about, I would go to that particular thing that give you an idea about. So you have a problem in hand that you would like to address, and how would you go about it? Obviously the problem, then you need to understand what is the physics behind that problem. Okay, so once you understand the physics behind the problem, you try to see how you can actually define the problem in terms of mathematical tool. So that's where the mathematical tool comes into the picture, or rather the governing equations that you always talk about. Then is important part is that these numerical methods that is you are talking about here, this is where these different kind of CA techniques they come into the picture, which you talk about. I mean, you have been kind of given told about FD, FV or spectral, something like that. So these important portion is very, very crucial. Then you need to bring in your geometry into the picture. So once you bring in the geometry into the picture, that should you comes the grid in CFD you call it, and then obviously the idiots that you have for you, that's the computer. I always call they are idiots, because the set of instructions that you give to those idiots, they are going to perform the simulation for you. So if you provide a wrong set of instruction, they will give you junk. So this is where you have to be extremely careful as an engineer, where you talk about that, then finally you analyze. This is what closes the whole loop of the CFD. If I look at in a nutshell, this is what I call it personally, try to call it as a CFD. Now, obviously, I mean, this kind of given already been a heads up that what are the different stages of CFD. So there are primarily, I mean, I categorize them in 3 different stages. One is the pre-processing stage, one is the computation stage. This is where your supercomputers or the HPC environment or the all other high performance computing environment coming into the picture, and this workshop is specifically for that. And then finally the post-processing. But if we don't touch upon the other 2, only doing the computing doesn't make any sense for a CFD, because what is the purpose of your CFD? That you want to solve a problem in hand, which is a realistic problem or the engineering problem or scientific problem, how you define it. It is there in your hand, and you try to look at through your all these models, whatever models you talk about, then you get the solution done. And then, so it's more like not a single shot process, it's more like an iterative process. You go through these iterations and get the solution done. So this closes the whole loop of the set of environment that you are in. So obviously these are the things that I would not say that going to talk too much about this. I mean, I'm assuming that you people have some background about CFD, how they are being kind of, so this has a whole range of applications. If time permits toward the end, I'll give you some applications where the HPC has been extensively used these days, and it's actually contributing the all sort of different kind of areas where the designs are done based on the CFDs. And one of the, if I have to give a realistic example right now, if you have or aware of this BrahMos missile, this was primarily designed using CFD. So later on the ground testing was done, but the whole design came up through the CFD. So this is the power of the CFD these days. So, okay, I mean, these are something that I assume that you know all these things, obviously the advantage. But what is important here to note, that why we are always claiming that this is much more powerful or complementary, but at the moment I am not committing anything that you get rid of experiments. That's not the point here. Point here is that you should complement each other. That's where as an engineer or scientist you would be able to contribute in the design process. End game or the aim of yours is that to design something. Okay, if you want to design something, then they should be complementary. But what it does that, I mean, why do you want to spend so much of money? You talk about an, let's say give you a very, I mean, example of aircraft engine or the whole aircraft. Do you think that you are going to make certain, obviously that if you go by parts and you are going to test it, then change the design, come back and test it, it's $1 million wastage of money. No engine manufacturer or the aircraft manufacturer would not like to invest that much of money. So the way out is that they come up with the initial design with the CFD, or even sometimes even the aircraft industry, I mean specifically I can talk that they use even the 1D modeling or zeroth order modeling to come up with the preliminary design. Then obviously these days the CFD and HPC, they give that flexibility to come up with the initial sizing and all this, then you fabricate and go for testing. Then you come back and do a little bit of whatever modifications you require or sort of an optimization, then you go back. Okay, and then the final product comes into the picture. So obviously, I mean, just to note here, I mean, if you think about CFD in the early days, 70s or 80s, and we have reached in a different stages. And right now we are not talking about, I mean, those days when people are doing those early days talking about CFD, they didn't have I mean, now your laptop is quite powerful to get some simulation done. But those days, even those computers which are available, it's not possible. So obviously this curve is not updated, it should have been updated. So but even if you look at the trend, this is what the flops that we are talking about. petaflops, exascale computing, and that's what the purpose of this particular workshop is about. That we have, this is where we are heading, and that's where, as an CFD engineer, and that's what I started off, that CFD has matured enough, because you should be talking about how you can improve your performance, how you can use the power of the architectures, because every day there is a change in architecture, more powerful architecture coming into the market, then how you can make it scalable and how you can use that power that you have in your hand. It's rather than writing, okay, I mean, these days even writing a small CFD code in a classroom project is just a normal process. I mean, even 10 years back or 12 years back, so when I started my career, probably it was not even thought of. But today, any CFD class and other things, I think even yesterday, Professor Samnath was talking about, people can do even small MPI programs, and that your laptop can perform that. But that's not the idea about actual design problems where you are heading. You should be talking about hexacle computing. I mean, then you need all these petaflops and whatever machines coming into the pictures. And we have, under this NSM, thanks to the government, CDAC and everybody, so that these machines are coming across the India, different places they have been installed. So we can really do real meaningful calculations. So if I have to close that loop, how problems are addressed, so I'll just quickly run through that. So basically you have a problem in hand, physical problem. So you finally identify the problem, and during the pre-processing stage you have those grid generations and all these things, and then you set up the problem for the computer and get the solution done, and finally you do the post-processing to come up with the solution. Obviously, this is a very, one of the statement that I always like to have. It's a tool that requires your switch on your brain, okay, and your fantasy, what you can think of. So we talked about, so these are the different stages, and every stage gets involved in using those multi-core systems. Even in the pre-processing stage, if I have to say these days, if you talk about few millions grid points, I mean, you can generate those grids even in a multiprocessor system, even a serial machines. I mean, we also encounter this problem and we do that. So you use the grid generator in a multi-core system so that you can generate a million cells grids. Obviously, this is where the HPC comes into the picture, finally the results. So here, the whole idea here is that you have this problem in hand that you want to solve, and then you have these analytical tools, or the different methods, and these are some of the methods which are listed out pretty much, I would say, the ones which are quite popular in the CFD community, they are there, and obviously today's session we are going to talk about this, because you have been, I think tomorrow finite element is going to be talked about, Professor Siva, you have been already given spectral and finite difference. So this is where things come into the picture. You have a problem, you put your mathematical tool and the discretization tool, that's a different methods. So we talk about different methods, every method has its own way to get things done, or rather the implementation, and end of the day what you get, the problem, physical problem, which is a set of governing equations, then you apply your different methods, then you get what you get after applying these numerical methods, the discretized equations, or in terms of a linear system. So this is where you need your computer to solve that problem, and once you solve that problem, okay, rest is your. So obviously, I apologize if I missed out anything, but these are available things which are, different community, different academic researcher, they use their own in-house codes. Then you have some of the commercial codes which are quite popular. Obviously, there are plenty of, as I said, the list can be endless at this moment. There are plenty of open source softwares which are one can go at. But today I will give you some flavor of how this finite volume are implemented in open form framework, so that you get to see things how it works. Obviously, these are okay. So with that note, let me get into the actual part of the finite volume, how you take care of that. So if I just to again switch your brain, so I just reiterate the process. So I have a problem in hand which is represented by the set of governing equations, then I apply my numerical methods, and then I get a system which I have to solve it using my HPC environment. So this is what now we are going to talk about. So I bring back that the whole slide again in a different form. So I have pre-processing stage. So that means my problem statement. So this is very, very important because I have to have my problem statement. I have to identify the governing equation that's going to govern that particular problem. Then I need to do this meshing or discrete, the grid generation, which I need to take care. Then I come to the processing stage. This is where I make use of my HPC environment. So the set of PDs that I have, that is where I apply my different methods. Then I get the final system of equation that I need to solve, and then finally the post-processing stage. Okay. So when I talk about that pre-processing stage, then it involves a different range of problems or different range of things. Because when I say even generate a grid across this particular object, it could be in multiple ways. So one can have, broadly, if I have to classify, you can have the structured mesh or you can have the unstructured mesh. Why I am talking about both structured mesh and unstructured mesh here, the reason is that this is going to some extent lead to a kind of a solution methodology that you have, or if I put it in a nutshell, solver that you have, how that's going to behave. Because if you have, this, anyway, I'm going to touch upon again in the afternoon, but you can have two different category of solvers. One could be structured solver, one could be unstructured solver. And this is where the structured and unstructured solver, the way they are mathematically formulated are different. One structured solver, the way you can think about hierarchically, I could put the unstructured solver little above the structured solver, because this is structured solver is a specific subset of unstructured solver. I'll come to that and you can see why, because the unstructured solver can take also the structured grid. So how your solver is designed or you have developed, how your code is developed, that's going to immediately tell you that you cannot invoke a structured mesh or unstructured mesh. If you have an unstructured solver, definitely you can take care of all these different grids. That's what I will re-emphasize, the unstructured solver can take care of everything, so which indirectly tells me structured solver is a subset of the unstructured solver. If you have a structured solver which can only take the structured or this kind of body fitted grid, but it cannot handle any this set of the unstructured solver, which I can say this portion of the set of grids which are there, so you cannot handle in your structured solver. So that means this becomes little stingy in that sense. It doesn't give you the flexibility. When you go to an actual real life problem, the problem of interest that you have could be really complicated. It could have a lot of curvatures. Then generating these different kind of unstructured grids could be probably handy, but your solver has to support. So if your solver doesn't support, then this is of no use for you. So if I have a solver which is based on unstructured grid, then it can handle even structured grid. Now, what kind of grid I will generate or not, who would decide that? You would decide that as an engineer. That is where your experience, your experience in CFD use or CFD field would come into picture, or rather becomes handy, that you have to be a judge of that, what kind of grid suits my particular problem. The problem to problem you go, the different kinds of grid could be useful. Some cases I can tell you this kind of grid is quite handy. Some cases I would prefer this kind of grid. Let's assume I have a powerful solver which is an unstructured solver which can handle all different range of grids, but probably some flows I would prefer this kind of grids, and some case I prefer this kind of grid, some case I would have a prism or triangular. So idea is that your solver would dictate what kind of mesh you can generate. So even in the pre-processing stage that you are going to spend your time, you have to have an idea about what your solver is all about. If your solver is not capable of handle the unstructured grid, then you are out of this loop. So you are only can generate structured grid. I am never saying or committing that this is not doable or that not doable. So there are different ways one can handle, but end of the day it again comes down to or boils down to the same thing, that what kind of solver I have. So everything finally boils down to the what is the environment that you have. So that actually gives you an idea about what kind of grid that you can generate, and then you can actually perform your simulations. So this is what the different grids. Now I come to this when you talk about the grid topology specifically in terms of finite volume. So you have different grid terminology. Okay, these are now very specific to finite volume. So let's assume a simple two-dimensional structure so that it is easy to conceive. You have a cell center, which is always termed as a cell center. Then you have all these vertex, and then you have the faces. Okay, and if you talk about, so this is a kind of an topology that or the nomenclature that you use in structured solver. So this is not unstructured solver. Okay, let me be specific here. So structured solver also you can formulate in two different ways. One can be this kind of environment, which is called the staggered grid environment. So staggered grid, I say why? Because if you can see this, all my scalar quantities which in pressure, any temperature, species mass fraction, all these are stored in the cell center, which is the same notation, and my flow fields, the velocity fields, u, v, w, if you have three-dimensional system, so they are actually always in the faces. So that's what it says staggered, because some of the quantities which are very specifically the scalar quantities are in the cell center and everything else in the face. So when you talk about finite volume, always you talk about a finite, small cell. So this is what we talk about, a cell. And then there is a cell center, there is a face, there are vertex. So my velocity components are defined at the face, scalar quantities are defined at the cell center. That's what the staggered arrangement we all talk about. And as soon as you do that, then every finite cell that you talk, they are going to be identified in this fashion. So that means if I have to come here, then this is what is used for your scalar, and that is what is going to be used for one of the velocity component, and then the other one is for the second velocity component. Because if I stick to that two-dimensional environment, then you have a u component, then you have v component. So the cell definition actually, so for any variable that you would like to solve, you should have a cell, because the one of the advantage of finite volume over finite difference, I would say that all the properties are conservative. The solution method is conservative, because every property quantities that you are going to solve, they are conserved across this small cell. That's what it's called the finite volume, because that's a finite cell and everything is conserved. So all it just you think about in a simple thing. If any given point of time I have to say that the number of attendees here to be constant, and then both the doors are open, these are my faces of the cell. So one can come in, one may sit on, the other one may go out, but then always the conservations of the entity. If I specify that, then whatever comes in, that has to go out to conserve that. So this is what happens in finite volume. So whatever comes in, it has to cross the boundary, so that flux conservation. So advantage here is that in finite volume, the variables that you are solving, obviously in terms of u, v, velocity, scalars and all these, they are conserved across that small volume. So that's what it talk about the staggered grid environment. Then you talk about your collocated grid environment, where obviously it differs from my staggered grid environment. Here life is much more simpler. I don't have to worry about too much. Whatever I have, I'm going to dump inside the cell center. So which means starting from my velocity component, pressure, temperature, species, whatever I have, everything I will solve in the cell center. So immediate question arises, which one is preferred? Okay. It depends again, I mean both are acceptable, different solvers are developed over the time, different groups uses different kind of solver. They could be of either of these two ways, either collocated ways or staggered ways, provided they are structured solver. I am not talking here unstructured, I am coming to that in next few slides. So once you talk about structured finite volume solver, it has to be only two categories. Either it could be collocated environment, that means everything I am going to solve in the cell center over, or I could solve in the staggered way. It has some advantage, it has some disadvantage. This is obviously slightly preferred because this gives you better some numerical instabilities, let me put it this way, it arises from the mass conservation. So once you go to collocated environment, there is a possibility, not guaranteed, possibility there could be issues or instabilities which might arise due to your some boundary conditions or the flow conditions that you are trying to solve. Those instabilities can be avoided or eliminated if you go back to staggered environment. So that's why it is slightly better preferred. But having said that, it's not that the collocated is not working or it's not workable, that also widely used, but those cases are very, very specific cases and very specific to a problem dependent, where you may come across that kind of instabilities. Okay, and it may so happen you may be lucky enough to get over that kind of situations and your solver runs through fine. Okay, even a small example, if I have to take, let's say even a flow through a channel, which is probably the simplest of the lot, which I know the solutions, analytical solutions, even a laminar, let's say Reynolds number 100 or 150, 200. This guy would be probably working fine. Sometimes this guy may give a problem for that simple problem because the kind of boundary condition I have due to pressure driven flow. But it is again very, very sensitive how you have discretized your grid, or rather you have these small finite cells that you have generated for your solver and things like that. So maybe you have a large amount of grids or the grid width is quite high, then possibly you may have that. If you have a small grid size and things like that, you may come across or come over that kind of situation. So take away message, structured solver could be of two types, either it could be staggered environment or it could be collocated environment. Okay. Now I come to the solver part. So when I come to the solver part, there are different things that you need to do. One is that what are the right approximation. When I say right approximation means there are, if you see, some of these bullets are heavily dependent on my actual flow problem. Whether the flow is laminar or turbulent, that's going to dictate what. So that means I have to take that into consideration. If it's a laminar flow, I'm probably well off. If it's a turbulent flow, that immediately says I need some turbulence model to handle that kind of turbulent situation. So without having a turbulence model in place, I can't handle that. So that's what it's going to take. Problem, what kind of problem I'm going to solve, so that dictates whether I can solve that in a steady mode or unsteady mode. There are problems, let's say flow through a channel, 100 Reynolds number. What mode should I use? Anybody guess? Steady, unsteady? Steady is good enough, right? I can do unsteady, shear wastage of my resources, eventually it's going to reach steady state. Okay? Let me take a problem of flow over a cylinder, Reynolds number 60. Very, very specific to Reynolds number 60 or 70. So, what solution strategy I should adopt, steady or unsteady? Unsteady. Why? Any guess? So, yes, absolutely right. The reason behind that, your flow has inherent unsteadiness. There is a vortex setting, counter rotating vortex pair which are getting generated. So once you have if your flow is inherently unsteady and you apply a steady solver, what are you going to get? Nothing but junk. So like your chips. Okay. So that means you as a scientist or engineer, this is where you have to use your upstairs, which has God has given you. Can't do things blindly. Okay, if you do things blindly, it will become colorful fluid dynamics, not computational fluid dynamics. So my sincere advice, stay away from that colorful fluid dynamics, which is a trend or alarming trend in the community. Okay, so then certain problems I can use viscous or I can take inviscid solutions. Okay, so that again dictates you or tells you what kind of problem in hand that I have, whether my inviscid solution is good enough or not. Okay, it's again all these parameters. Then multiphase, probably I can list some more reactions, buoyancy driven flows, all these, it can be again a big list. The idea here is to give you an understanding that these are all again physics based information that you have. So this physics based information is going to tell you what kind of modeling approach I should adopt. What are the extra governing equations or conservative equations that I should take up. If I don't take or consider the correct set of equation, let's say I solve a flow over an aerofoil at 6 million Reynolds number and I use laminar flow. Again I am going to get a packet of chips, nothing but then. Okay. So these are essentially your physics based information that you need to incorporate in your solver. Then comes to the modeling of the equations, which is again a standard set of governing equations, and you have all sort of conservation equations starting from your mass conservation, continuity, momentum equations, energy equation, you use equation of state depending on the flow problem, turbulent equations, again when I go to compressible you will have some more. Okay, you solve the reaction system, then you need the again individual species mass transfer equation. You go to magnetohydrodynamics, you need some more extra potential equations, so there could be more. Then solution of the equation. So as I said, when you apply this method, end of the day you get the set of linear system, that the size of the linear system that you are, that is where the scalability and all this of the use of the environment which is going to be powerful. Again this list is not an exhaustive one. Again emphasize, you are taking notes fine, but these are not all. There could be a lot, then I can't fit in my slide. So there are again two ways you can solve those linear systems. So understanding of the linear algebra is an utmost importance or requirement for a good CFD engineer. Without understanding a linear system, using this linear solver is a crime, because you don't know what is going to give you. As I said, you are fitting the set of instruction to the computer will give you some numbers. Whether those numbers make sense or not, you have to make a call. You can get some numbers, but the numbers doesn't make a call. When you look at a food, you decide, okay, this one is good, today breakfast I have this, I want this or I want that. Okay, you make a call, right? Your brain immediately triggers. So same thing here. Without understanding this, so that means you have to be very good at linear algebra, vector space, linear independence, different kind of single value decompositions, whatever you talk about. So then either I can solve those methods, the linear system Ax equals to B through direct method or iterative methods. Again, which one is preferred? So my answer to that is that I will not give you a specific answer. I will always leave it open. Depending on the flow problem or the problem in hand, I will decide which one to go. If I am solving a channel, probably I would prefer a direct method, because I would be handling 100 by 100 in a two-dimensional system. I go to a flow around a aircraft or wing or engine or something else, it's a few millions grid point, millions by millions, and then multiplied by the degrees of freedom of your variable. If you are trying to do that, probably you are only, not crime, you are only fooling yourself, nobody else, because that's going to consume your years after years. So the best method that time would be iterative methods, and there are different variants of iterative methods what you can adopt. Performance of these methods are extremely sensitive to the kind of linear system that you have. Why I am saying linear system is very, very important or crucial to note here, because your matrix is a sparse matrix. It's not a very nice looking matrix. So the sparse system, so your matrix has certain properties. So those properties, that means your eigenvalues of those system is going to be very, very crucial. And there is a call spectral radius of that system is going to dictate your convergence of this linear solver. So those things one has to understand when you talk about these linear solvers, because one can go through. There is a nice book on the iterative methods book by Professor Yusuf Shad. One should read if you are really serious about CFD. Go through that book. It's available even free PDF in the internet. It's something you should have a Bible if you are serious about CFD. Otherwise, forget about it. You can ignore my statement. Now, again coming back to this, you need data visualization. So probably this you will get some exposure during the hands-on session. You can use MATLAB. There are origin flows, studios, take plots. I mean, there are different things one can use, whatever you have access. This is free. This is not free, obviously. Origin Pro is not free. RStudio free. Take plot is not free. Excel is obviously not free. Sigma plot free. So GNU plot free. So you can use all these different things. So now little bit core into the problem definition. So I have all sort of general governing equations, and if I put this in a I have the term, the unsteady term or the time discrete. Yeah. Okay. So I think that's better. So this is ParaView is kind of free, RStudio free, Sigma plot free if you have GNU plot, but MATLAB, origin flow, take plot, these are not free. Excel even it's not free. So now I come here where you see this particular term which I talk about, the unsteady term, then you have that flux term, then you have the source term. So this is where you categorize the whole governing equation in three broad system, and the terms that you can see here actually that you can, how these terms are actually discretized in the finite volume. So you take a small finite cell and you integrate over that cell. So whole idea is that you do the conservation, and then once you do the conservation you get the discretized system which may look like this. Okay. So if I do a little bit of step jump here straight away, so I have all these terms which are unsteady term, then convection term, I have diffusion term, then I have the source term here, and this is how the now this is where I am getting you a little bit introduced to the unstructured system, and you see this particular grid is sort of having an how many faces? 6 faces, so hexagonal. So all these phases that where you have to do the flux conservation, and this is how typically this is implemented in open form, and this implementation is quite looks straightforward. Obviously the environment is different, so I leave that pre-processing part slightly away, but if you look at, one can map the term very easily. If you see this term mapping here, so each and every term you can correlate. So this is the unsteady term, the first term, then the second term your convection term, this is your Laplacian operator which uses your diffusion term, and then finally if you have any source term. So this is where OpenFOAM gives you that flexibility or idea about using those. Obviously when you talk about this parameter FVM or FVC which you see here, they means a lot. Okay. So FVM is and FVC, they are talking about whether it's in the cell or in the face or the surface integration that you are doing, and all these different types of operators that you can do, right? I mean the interpolation operators and then different kinds of discretization scheme, time discretization scheme, and then divergence calls and all these things. But there is a hierarchy sitting there where all the class definitions are already there, then you use those class definitions. So you don't, I mean if you want to explore these, then don't need to kind of reinvent the wheel, use those class definitions, then you can modify, and the definition is that way straightforward. So if I have a new equation to be solved, I can always nicely fit into that environment. Obviously, when I say nicely fit in, the implementation part would be not that nicer, but it's absolutely doable. And this definition of these classes would give you that flexibility to do that. Now, once you implement those things, then immediately comes one important aspect of boundary condition. So there could be one hand whether, I mean, you can see here where the first one, when you have the, it's called the discrete boundary condition. That means I'm talking about a very generic variable in terms of phi. The phi could be anything. It could be u, it could be v, it could be w, it could be t, it could be pressure. So any variable that in a finite volume approach, this is the way you try to define the boundary condition. So it's a discrete boundary condition. That's even a standard one in any CFD. But in a finite cell, the cell boundary will have that cell sitting there. Then you need to properly modify. So if I go a little further, whenever you apply a boundary condition in any CFD method, obviously the boundary cells or the boundary faces or the boundary points or the boundary nodes, you have to treat separately. You cannot club them with the interior nodes and the boundary nodes. So same thing goes here, that you need a special treatment. So you do this is for the Neumann boundary condition, then accordingly you change these coefficients. Similarly, you apply the Neumann boundary condition, that means the gradient is provided. So once the gradient, that's called the Neumann type boundary condition. Once your gradient is provided, then accordingly you modify these coefficients. Okay. So every cell, I will use my discretized equation, then I come up with a set of equation system. So the equation system would look like this in a finite volume approach. So this is again, one can think about those C, W, N, S. I think the C is your boundary cell. C could, I mean, then the equation system for interior nodes and the boundary, the equation system looks like same. Only thing you modify those coefficients in terms of A. Okay. So every cell, the categorization is that it's a very natural categorization: east face, west face, north face, south face. So that makes my life easier. So when I say AS, that means south face. When I say AN, it's a north face, A east. So as soon as I go to boundary, I identify which face is that. That's the coefficient that I have to modify, and I implement the boundary condition. So this is how it is taken care of. So finally you come out, I mean, this is the equation, so I don't have to go about it. So equation that you solve, and so once you discretize this momentum equation, so different terms you discretize. So I mean, just to take a small cell here which is highlighted, and that across that cell, which I said that, and every east face is marked as east, west face is marked as west. So if you say that's a one dimensional stencil, then you do the integration and get the mass conservation done, and then finally get that equation system. So if I connect that thing with the open form, so this is my governing equation that I have here. Okay, then this is my unsteady term, and this is the term which gives rise to those different coefficients. So these are the coefficients that I need to, I mean, obviously I need to calculate. Okay, and so I'll go term by term here. So that's are my set of equations: continuity equation, U component, V component, and W component. And then I have all these different operators for the pressure and all these. And this is the solver. Probably you will go through the hands-on, and it is a purely incompressible solver. And this is where the loop starts. It starts with the loop, that means the outer loop of the solution. Then you first calculate your stability of the system using the Couette number calculation. Then you solve the momentum equation, and then you go to the pressure corrections where you do the mass conservation, then go over the loop and get the solution by getting below your error limit in certain tolerance value. Okay. So the whole solver, if I put it back, so that's my piezo loop which works. Okay. And these are the all definition of variable. So whether it's a scalar, vector, tensor, that way, and this is the corresponding basically the coefficients that you need to update. Okay, so this is how once you go through the hands-on session, you will get to see these are exactly the same notation. So that does the interpolations, and then you. So this loop is what it is doing. If I have to say that, it's doing your mass conservation in this loop. So in an incompressible scenario, I have my continuity equation, I have momentum equation. So the way it solves, so let me give you quickly an idea. So there is a pressure field which is sitting there in terms of gradient. So I start with an assumed grace pressure. So I solve the momentum equation. I get my component of velocity, but they are not correct. As soon as I fit into my continuity equation, the mass conservation is not going to be satisfied because my pressure was not correct one. So once that is not there, that going to give rise to a pressure Poisson equation, which is in terms of Laplacian equation in terms of pressure correction. That's what you call it in incompressible finite volume. So that pressure Poisson equation is solved in this loop, and all these coefficients which are kind of connected that pressure correction equation. Once I get the pressure corrections, using that I will correct my flow field again. Then obviously that pressure correction is going to guarantee my mass conservation. Then I move to the next cell of iteration. So this is how the whole incompressible solver works. So beginning I start gauge pressure, get my momentum calculation done, which is not correct. Check your continuity is satisfied or not. Continuity is not going to be satisfied. So it gives rise to a Laplacian operator or Laplacian equation in terms of pressure correction. Solve that, and the source term in the pressure correction would be your imbalance in the mass in that particular small cell. That source term, using that source term, solve the pressure correction. So that corrects the pressure, move to the next level of correction in the flow field, then goes in the whole physical loop of iteration. This is how the whole system works. And there, these are the different schemes that would be available. When you will go through again in the hands-on, you will get to see that DDT schemes would allow you to choose the different time integration technique. There are different on. This is Euler is the first order accurate scheme. There are second order accurate scheme or Crank-Nicolson, things like that. You can implement your own because these are implicit schemes. So I have not gone into what kind of time integration that could be implicit or explicit in nature. So you can implement an explicit one as well. Then you have to modify the whole set of equations or solution strategy. But then you have a grad scheme, then divergence scheme. So these are the operators which are readily available in OpenFOAM framework. So if you want to write an extra equation or you want to solve a new problem, you need some new equation to be implemented, that way it's handy. And the back end, the important part where the HPC is coming into that, the parallelization part. So that is already taken care of. Okay, because the whole OpenFOAM framework is parallelized. So then once you implement that in a modular fashion, so that make use of that parallel environment, and you can actually fire the job in a multiprocess system. Okay, so that's what it's now. So these are the, again give you an idea about different linear solver. So this PCG is the precondition conjugate gradient. So there are, and then what are the input controls? So this file here, which you see the control dict file, that's the input file. So I as a user specify, it's not you go and change in the code. Solver, once it is ready, everything is controlled through the input, and that should be the idea of any CFD code. You cannot go for problem to problem and change the solver. It should be input control. And once you talk about input control, then these are all the different input files. So there are, again, these are some of them which I can fit in the slides, but there could be some more extra that you can bring in. And top of that, which allows you to compile your own library, object-oriented library, and you can bring that in this input in terms of FSIs, in terms of any other higher-end multi-scales coupling. So you can bring in those modules into this input file, but you have to pre-compile that and then get it. Okay. So almost towards the end. So these are the problem that is a plan, how much you could do or the TA could also carry out, that let's see. But this is what your kind of plan is, that you will go through all these problems, or you would be try to solving this problem, try to visualize the data. Even I would request that you start with one problem, completely do, so that they visualize the data, then move to the next one. It's not that you have to finish everything. If the time doesn't permit, don't push hard. That doesn't serve the purpose. Okay. So with something else, I'll end my talk and take up the questions. So just to give you an idea what kind of applications one can think about. So this is the different range of industry where is not CFD used. So starting from the aerospace industry, appliances where CFD used as a design tool. You go to automotive industry, heavily used. Talking about their external aerodynamics, that's what the looks are becoming very nice. Not my images, all internet image. Biomedical application, that's the another area where CFD application is becoming extremely important, or rather it's emerging with a rapid space. You come to chemical processing industry, use of CFD been there for quite a while. I mean, I think couple of decades old. You go to HVAC, that means your air conditioning, these are design purposes. You are sitting in a nice environment coming through these ducts and all these. Hydraulics, ship hydrodynamics, dams and all these, where civil engineers can be quite handy, mechanical engineers could be handy. Marine applications, oil and gas, power generations, and sports, which is another area where you can look at the aerodynamics of shuttlecocks and things like that. Now, slightly just to end with that, we are working on in our group on different kind of problems, and just to give you a glimpse what range of problem we actually solve where we use the HPC. And you see the kind of, this is probably in the smaller size when we talk about 0.1, and the runtime you see when we fire jobs in 48, 50, 64 or 96 or 100 processor. And with probably the new architecture which we have recently under NSM. So that kind of, because it's the three-dimensional, such a unsteady flow. So then we do a lot of this kind of fluid structure interaction problem. This is a multi-scale where I talked about here the both finite element solver, open form solver has been coupled, and the TA who is going to do that, he is the owner of this work, not me. This guy has graduated, he was one of the old master students. So again, this runtime was low because of the Reynolds number was low. Then this is another where we have used our in-house code and get immerse boundary technique to look at this kind of airfoil pitching dynamics. I mean, these are multiple papers which are out there, and there the runtimes again 2 days to month, depends on what is the scale, because then this was again these are all incompressible applications that we have been doing. This is where turbulence comes into the picture. So again, you see it's more than 2 months. I know you go to compressible, there is an order of magnitude change in the calculations. It's a few months where you have to sit on and just wait that the calculation is going to run. These are again some sort of turbulence modeling things that we have done earlier. So this is also a flow over a tubercles. This is Reynolds number is quite high, and it's more challenging in the sense because it's in the transonic zone, neither turbulent. So we came up with a hybrid RANSIB, and there the runtime pretty much 3 to 4 months straight away, no compromise. Once you resolve the boundary layer with a y+1, it's all taken care of the time. So these are the different codes that we use. Obviously, some of our in-house, our lab, we have the own resources, but heavily now banking on this NSM Param Sangnak cluster. So we have a multi variant of solvers based on our in-house and OpenFOAM, but heavily on OpenFOAM. We have developed our modules, multi-scale in noise and things like that, which I'll show you some of the compressible pictures in the afternoon. But these are not readily available in OpenFOAM, to make a note of that. So if you try to search, you will not get it. So this one has to develop. And when I talk about this is how the scalability of our in-house solver. And this is what we did when our Param machine was purchased and I was part of the scaling. So Obviously, you have been already introduced with the MPI, so I don't have to go. There is a strong scaling and the weak scaling. So this open form scales even when finally the vendor who is going to supply that. Initially it was ISC. That time we are involved, and this one has taken up to 400 million, and it scales quite nicely. And this is the scaling law that you come up with that. And the red line is your theoretical curve. So it scales nicely, but problem has to be of that order of magnitude. You see 20 million, 100 million, 400 million. If you have a less than 1 million, few thousand cell and you fire in 40 processor, it's a sheer wastage of time and resources. That doesn't require that. Because more than doing computing, this is where flops comes into the picture. Computation, you waste time in communication, in the MPI communication. So you have to be again a good judge of that thing, that what is my system that I have in hand, what processor I should take. Blindly, if you keep on increasing the number of processor, doesn't guarantee you are going to get good number of scaling. So that's another good take home message. So I like this word to conclude. So it's a powerful tool, and time and all this has really come down. So it also provides meaningful results with zero engineering interest, but so it's a common pathology. So you have to be fully conscious, right? And if you are God, then you think about train to the full resources, link the. So however you have more robust and efficient code, it's always important to estimate each point of view of your solver or project you want to obtain a result. It's not a blind. So you need your care, utmost care, switch your brain, use the judgment, what you need or what you not. So it's not colorful fluid dynamics, okay? And very important, no one believes the CFD result except the one who performed it, that's you. And everyone believes the experimental results, not my word. Dr. Roach, who is still alive, is a famous guy, who has a nice book on verification and validation of CFD. You should, even if you are interested sincerely, should read that. People do validation, think about his code is good. No, verification is something different. You don't look at your, see, I say my implementation is second order. End of the solution is not going to be second order. It could be, always it's lower than second order or fourth order. That's what verification is. So you should do those. Fajigar, unfortunately we lost him. He was a faculty in Stanford. There is a nice book on Perry and Fajigar on finite volume method. So the disaster one can encounter in computation is not the instability or lack of convergence, but the results that are simultaneously good enough to be believable, but bad enough to cause trouble. So if you fail, that's better. That's the message. Essentially, all models are wrong, but some are useful. So that's how I'm going to end. So identify your competence, use your sense of judgment, then use the CFD tool. Not, otherwise not. Thanks for listening, and if you have any question, I would be happy to take it up.
There are some questions from the online participants.
Okay.
Okay,
So,
I will read out for you. Give me a minute. The first question is the NS equations shown in the PPT is for only stationary reference frame or for moving reference frame as well?
Okay, the question here is that the NS equation that I have showed here in the PPT, it is for stationary reference frame. When you go to the moving reference frame, the system of equation will remain there, then the source term would come into the picture. So everything sort of, in other way one can think everything is there, but the source term is going to be coming into the picture once you have the moving reference frame. So some correction has to be made in the fluxes and all this, but the equation system pretty much looks same. Source term is not there because I have not shown the finer details of those source term. So problem to problem you change, then the finer details of the source term is going to change.
Okay. The next question is classification of grid, staggered, oblique, co-located are applicable to unstructured meshes as well?
No.
Okay.
Because unstructured mesh, the thing is that everything is sort of defined inside the cell center, and then you do the flux calculation. So unstructured solvers are all collocated.
Okay. The next question is, please give some information regarding ways to learn open form programming.
Okay, only by getting your hands dirty, nothing else. There is no easy solution. Only you need to start working from today, then probably after 6 months you can come back. First thing to start with that, how to get OpenFOAM installed from source code, not use those pre-installed version in Ubuntu or in Windows platform these days. Use from the source code and install it. That would learn you a lot. That would teach you a lot. Probably that would be the starting point. After that, solution comes.
Okay. The next question is, which software is given to better results for Rayleigh-Bernard problems between ANSYS and OpenFOAM?
Okay, so to be honest, I cannot really answer this question because I am neither having expertise in Rayleigh-Bernard conversion, neither on the, what is the other problem?
No, Rayleigh-Bernard problem,
okay, so
ANSYS and OpenFOAM, which is better?
I don't work on Rayleigh-Bernard convection, so I can't really comment whether OpenFOAM or ANSYS would be, which one is powerful or better. But obviously, I would like to, my last statement, not my last statement, you have to use your judgment. So everything is wrong, otherwise everything is correct. So it's who is using it, how you are using it, and I would add to that, even there are ANSYS, COMSOLs, and all these are also powerful software. They are doing $1 million, $1 trillion business. They are not bogus. They are equally powerful, but backend also they are solving these governing equations. One has to understand that. If you use that blindly, then you will only make it a colorful fluid dynamics, then complain about the solver. That can happen with any OpenFOAM, any open source solver, any in-house solver, that can happen. So it is the, again, sense of judgment, your experience, understanding, which would lead to some meaningful results.
Okay, the last question is, can we apply pressure velocity algorithms for shock wave problems?
Okay, Dr. Bikas wants to say something.
Oh, wait.
Yesterday, Professor Verma told for the class of problem like Rayleigh-Bernard convection, spectral based methods may be more accurate.
Because he has the strong expertise there. That's what I started with. I am not the expert in that. You talk about any fluid flow problem, probably I can comment more. So I started with that statement only. So the last
answer this question. Can we apply pressure velocity algorithms for shock wave problems?
Okay, so I would say that please hold on to till the second half, where afternoon I am going to talk about that. So probably I will say that keep your thrust little more longer, have your good lunch, then we'll come back to that in the second half where I'll talk about that. Yeah.
So with regard to transition problems, what is the state of art of the commercial solvers? So like, does it lack in any technical capability? What is the state of art?
The thing is that, see, I can talk about a little bit about ANSYS, I mean the Fluent. Fluent has some, see, the transition is a very challenging problem. So those who are hardcore transition CFD scientists, they prefer to do DNS and things like that, then that would come up with another set of problem, that then the solution methodology has to be really Cartesian based environment. You talk about a complicated problem like even with the curvature and all those issues would come. So if I leave that portion little aside, the best way to handle that, either you do resolved LES, which is again going to be equally expensive like DNS. So the hybrid methods are gaining popularity for that. Now that is where probably little bit ANSYS lacks, because they have some hybrid methods, but they are based on SST k omega, because you need RANs for the boundary layer, then outside the boundary layer you need the LES. So there you have, I think, SA based model, SST k omega based model, I think K epsilon based model. But in the transition, my experience again, that these are the models, they don't work. You need a good transition prediction RANs model. That's what we implemented, KK omega based model, which solves 3 equations in the RANs. Then we couple with the LES.
Thank you.
Sir, does mesh matrix play an important role in the accuracy of the results? And how much importance we have to give to mesh matrix in especially in large AD simulations?
So the question, let me reiterate if I have understood correctly. So the idea about the mesh size you talk about, right?
Mesh matrix like aspect ratio, skewness,
Yeah.
mesh
So
parameter.
the aspect ratio, skewness, all this, how much would that make impact in LES kind of simulation? They certainly do, and they play a huge role. First of all, in your LES, you should understand what would be my filter size. So for that you have to do some pre-computations. I mean the pre-computation in the sense a priori pen and paper, you go back to drawing board, do the calculations based on your Reynolds number. What is the scale of my range? Starting from my inertial range to my dissipation range, what is the scale I have? That would tell you, probably sometimes this bandwidth becomes this narrow. But then I have to fit my filter width there. Once you decide your filter width, your grid generation would be there. And typically, yes, to answer your question, they play a huge role. What we do, I can comment on that. We try to restrict when you go for LES, whether it's an incompressible or compressible range, try to restrict the aspect ratio 2.5 to 3, not beyond that. We don't go beyond that. Otherwise, it's going to, contaminate the solution a lot. Obviously, when you go to boundary layer, that poses a different challenge. That's what we go into the higher level of grids. But at the same time, if you are smart in grid generation is also an art. Actually, it's not necessarily, don't underestimate that. Probably let me be very thankful to one of my students who is going to run the TS session in the morning. He's a good grid generator. See, we also try to fit, let's say, I go 40 million cells. Now, my resource doesn't permit that. I have to think about what resources I have then, but I cannot compromise on the physics. Then you spend time, that's sort of months after months we spend in complicated grid generation, try to resolve the physics, but at the same time don't go beyond certain level of grids. 40 we try to bring down to 10 millions, and then we are okay to go ahead with the simulation resources that we have. Okay. Any other questions? Yeah.
Professor, there is a boundary condition in OpenFOAM which is called calculated. So which category does it lie in, like Dirichlet or Neumann?
Could you repeat once again, please?
There is a boundary condition called calculated boundary condition.
Okay.
So which category does it lie in? Means
say Neumann.
It's a Neumann boundary condition. So is it very similar to zero gradient?
Similar to zero gradient, but it takes certain cells inside or outside how you are defining in the input, in the boundary file.
Okay, and there is a function called correct boundary condition. So if we are applying boundary condition manually, so what is the usefulness of
the
that
correct
function?
Boundary conditions you have seen probably in my piezo loop.
Yeah.
What it does that, see, I am solving that Laplacian equation of the pressure correction. So delta 2 p prime equals to some source term which is the mass imbalance, right? Even to solve that, it's a elliptic equation. To solve a elliptic equation, I need boundary condition. So that correct boundary condition, that statement is an argument, I would say, in that C++. It will bring back your boundary condition that you have provided in the input file. So that's the argument which is going to bring the boundary condition that you have provided. So it imposes that boundary condition for that elliptical system.
In each iteration, does it?
Otherwise, that solution without boundary condition, any system of equation solution doesn't make any sense, right?
Yeah.
So it invokes that. That's the argument on that OpenFOAM class.
And my second question pertains to the staggered versus collocated grid. So as you mentioned, FEM and FEC means a lot. So can you explain a bit more about the application of staggered? Means which part of the code says that it's a staggered application?
Okay, so the one which I have showed, that's a typically that's a purely applications or implementation in the OpenFOAM. So OpenFOAM uses those calculation of those different terms of the governing equation, right? And OpenFOAM purely is an unstructured solver. So now if your grid is structured, it is automatically going to take care of that. See, unstructured, it identifies the mesh. It doesn't care about whether you have given a prism or triangle or hexagon or nice rectangle. So that's what I said in that particular slide. The structured solver is a subset of my unstructured solver. You provide that grid, it's going to handle it. but the reverse is not true. This is not going to handle. It's going to crash because your problem comes in the data structure definition. All variables are stored in certain data structure, right? I didn't touch those things assuming you have those ideas. So data structure definition is the important part. So once you go to unstructured solver, you have to keep track of the information of the cell, number of the cells or the position of the cell, all the vertices it has, how many, all the faces, connectivity of vertices to neighboring cell, connectivity of the face to the neighboring cell, all this information or that information matrix of a particular cell or finite volume to be stored. So data structure handling becomes much more expensive process rather than in structure. Structured solver, I only keep track of this next to next, this taken care of. I don't need the vertex. But here I need all this information. So now even if I provide a rectangular system, it's going to handle it because it treats the system in a similar fashion. Okay.
Thank you.
I think that is a question. So.
Sir, in the context of commercial packages like COMSOL multiphysics and ANSYS Fluent, ANSYS Fluent is a finite volume based software and COMSOL multiphysics is a FEM based software. Right now you define the staggered grid and co-located grid in the context of the finite volume way. Can you define the same staggered grid and co-located grid in finite element method, or we have to define in a different way?
The best person sitting there to answer that. I think that's your tomorrow session, but probably if you allow me a little bit to add, basically concept of finite element and finite volume. Okay, let me answer one thing here which I didn't touch. Usually I do that in the class. Finite volume does whatever it does here. Finally, when you come to those cells, you need to calculate these fluxes, right? How do you calculate these fluxes? Here, I can do that. Let's say I have a neighboring cell and probably, yeah. So this particular phase I need to calculate all the fluxes for the variable and all this. So I use the information of the neighboring cell. How am I going to do that? It's again Taylor series comes into the picture, and this is where you use indirectly what? Anybody guess? To calculate these fluxes, I am using essentially in there when I come down to calculation of these fluxes, I use Taylor series is a FD approach. FDM kind of approximation. That's what FDM, right? So inherently, finite volume is designed basis on that. Same thing you can do using FE also. Obviously, this will become messy. It will not be nice looking like what I am showing here. It requires a lot of involvement in terms of mathematics. So you have to be sound in mathematics. Otherwise, FE based finite volume is going to kill you. Okay? Am I right? It's going to kill you. So that's what we don't prefer that. So we are not mathematically strong. So we better prefer the simpler one, the FD based. So that's probably answer your things. Now coming back to slightly in FE also the approach is similar. You talk about a cell, you do the integration, basically you do the weighted residual. Then from here you use this, they call it the weight function or whatever different things, then you come down to, so he will explain that. I will not go more than that, otherwise I will commit mistakes. Okay.
One more. One more question. So like you discussed today for incompressible flow. In general, ANSYS Fluent, what we do, you use pressure based solver to solve incompressible flow. Then what happens is that sometimes the compressible fluid can behave as an incompressible flow. At that point of time, can we use the density based solver in spite of pressure based solver?
Again, I would request that you hold on to this, you bring back this question to me in the second half, that I will answer better. Because that time when I show you the different solution strategy, probably it would allow me to answer your questions in a best possible way, which you will probably conceive or appreciate a little bit more. I can answer this right away, but you will not be able to appreciate that because you need to see those set of equations, how that's tackled.
Thank you.
So the flux approximation there using Taylor series, if we truncate at a higher order, if we use higher order interpolation polynomials, how does it how does it fare with the FVM method?
So if I use higher order, then if you can second half, if you repeat. So since I am using
the effect on the stability of the problem convergence, will there be oscillations?
so you can always go higher order, and people do use that. I mean, simple. If I that's what the different kind of schemes are there. How I am doing that flux. I think some slide it was there. How I am calculating these fluxes, whether using these two cells, using cells ahead of that, whether cells behind that. So that increases the accuracy of your spatial discretization. So if you go for higher order spatial discretization, probably
No, that I agree with. Will I be able to get a converse solution? Will I stability?
You do. Yes, you can.
All right.
Yeah.
on. Hello.
Okay, welcome back to this morning's NSM workshop for day 3. So we'll now start with the hands-on session. So we have Mr. Mayank, who is a PhD student from IIT Kanpur, and he'll be doing the hands-on session on FEM for incompressible flows. Mayank, take over.
Yeah, thank you first. So hello everyone. So we will be having the lab session 1, that is on incompressible flow equations. So majorly I will be talking about problem number 1, that is a lid-driven cavity flow, which is a standard problem of CFD, and we will be solving it starting from the meshing and then like changing the schemes, then changing the mesh size, and then validating with the available results. Then I will try to touch upon the second problem, that is backward step problem, which is also an incompressible backward step. Then if time permits, we will see the moving cone problem. So let's start with the lid-driven cavity. So mostly I have sent you a zip file on this select channel. So all of you can download it because that will be handy for us to conduct the lab session. So you can download it. So lid-driven cavity, why we are studying like lid-driven cavity? So what is it first? We will like lid-driven cavity is a fluid filled in a cavity where the 3 walls which are in U shape are stationary and the top fluid is excited by a moving boundary, and because of the tangential velocity, the fluid at the top attains the plate velocity. So why we are using this lid-driven cavity? Because it's a very simple problem, easy to understand, and boundary conditions are relatively simple, and we can get some interesting and complex flow features from this problem statement. So these are the some physical parameters which are the flow parameters which we'll be using. So velocity of the plate is 1 meter per second, the length of the square cavity is 0.1 meter, and Reynolds number based on the length and the velocity is 100, and the kinematic viscosity of the fluid is 1 e⁻³ -3, and then type of flow is laminar and incompressible. So Professor Day has already discussed the steps to solve. So pre-processing will be done with geometry generation and then mesh generation. The processing will deal with the setting up the boundary conditions, setting up the physical parameters of the flow, and the solver settings. Then we will see the visualization of the contours by drawing the streamlines and seeing the pressure and velocity contours in ParaView. And then finally we will compare the line plots obtained from the simulations to match with the Gia's result, who has done it in 1982. So let's start with the Padam. I think you already have one login with you. So I will directly go to the MOVA Extram. So you need to connect to the Padam login for the lab session. So it's padamutkarsh.cdec.ac.in, and then you must have received one username. You can log in using like mine is 003, port is 4422. Then so yes, so it will ask for some captcha. So just fill it and then it will allow you to enter your password. Yeah. So it should look like your screen should look like this. Okay. So all of you have logged in. Okay. So we will go to the this screen. Then we need to load the OpenFOAM environment, which will be loaded using the bash RC file we can use. So just type this vi and tilde dot backslash dot bash rc and add these following lines. I will do it parallelly. So we will do vi tilde dot backslash dot bash rc, and then in the bash rc you need to press I to insert, and then you can type these 2 lines from source. Okay, I will go again once. So just type vi space back tilde then backslash dot bash rc. Enter. Now, okay. So when you hit enter, then it will show you this kind of a screen where you need to add these 2 lines. So you might not have these 2 lines, so you need to add it. You check somebody. Just press I and it will go to the insert mode. You can type it then. So everybody typed? Okay, so just press escape and then type colon WQ. You can see at the bottom. So it's used for write and quit. W means write and Q means quit. So just sorry. So when you hit enter, it will again come back to the terminal. Another? Go there. Did not get? Okay, I will again do it. Then we're typing these. Okay. So you have typed it module load. Okay. So I will just repeat in the beginning. So you are logged in, right? So just type vi, that is virtual editor, and then type tilde backslash dot bash rc. Sorry. Then hit enter, then it will show you some kind of a screen. Okay, then you need to type these 2 lines, source and module. So you need to press I, then it will go to the insert mode. Yeah, these 2, source and module. Check. Yeah. go there, export this arrow, right, press I, then it will go to the insert mode. Now you can type. Okay. So remove this I. Yeah, type those lines. Okay, VI space. Okay, thank you. Anurag, this is calling this. Yeah. Yeah, so we are done with this. So now you have already added like bash rc. Now you have to give the command to source tilde backslash then bash rc. So you will hit enter, then it will take some time. It will load all the libraries of OpenFOAM. Okay. So just check if OpenFOAM is loaded. You can type ICOF, then tab. It will autofill. Like if you type IC tab, it will show some files. So if icoform is there or not, you need to check. So you need to type ICF and then tab, press the tab key. It will autofill to form if it is loaded properly. So everyone is getting this icoform field. Okay, so now it means that icoform like openform environment is already loaded in your system. So basically the openform case has this kind of structure where you have majorly 3 folders that are mandatory. One is 0 folder which contains the boundary conditions as well as the initial conditions, and the second folder is your constant folder which contains the mesh informations and thermophysical properties and turbulence characteristic properties of your flow, and the third folder will be the system folder which will contain all the control parameters and the FV schemes, which schemes you are using, and whatever tolerance, what is the convergence criteria you are defining. So those things will be done in the system folder. So in 0 folder you might for incompressible, because we are solving for pressure and velocity only, so we will have only 2 files, one for pressure and another for velocity. So P file will contain the pressure boundary conditions and as well as the pressure initial conditions, and U file will contain the velocity conditions, we will see subsequently. Then you have constant folder where you have polymesh, where the mesh informations will be there, because it is solving in the unstructured format. So polymesh will have the information of all the neighbors, all the faces, points, zones, and the name of the boundaries. And the second file, transport properties, will define the properties of the fluid, which is usually the viscosity of the fluid, and then the turbulence properties, where we will define if the flow we are solving is turbulent or it is a laminar solution. Then system folder, block mesh file, we will write the block mesh file to generate the geometry as well as the meshing. Then control dict file, we will set the control parameters, and in FV schemes we will select the schemes. We will see these files subsequently. So let's start with the geometry definition. So usually this problem is actually a 2D problem, but openform is inherently solves in a 3D geometry. So the Z direction is extruded with a thickness with one cell. So it assumes it's a 2D flow. So this is the typical openform file header. So before this, I will request all of you to all of you have downloaded that zip file which I have shared on the Slack. So just upload it on your account. So I will show you how to upload it. Just open your terminal. Okay. Yeah. So just open your terminal, and then in the side, it's showing or not? Yeah. So in the side there is one option to upload to current folder. Right. So just click on it. It will ask for the file to upload. So wherever you have downloaded, just locate the file and open. So here you have one folder, upload to current folder button in the left side, and click, it will ask for the file to choose. Okay, locate the file where you have downloaded, like in your case I guess it will be in downloads, and then click on the file and click open. So it will upload the file in the folder. So this folder is actually home cfd003, which is my username. So this is the same folder where I have logged in. So if I will do the ls command, it will show how many files are there in the folder. Right, everyone have uploaded? So those who are getting some difficulty to upload the file, so they can try one thing. If this works, go to session, then SFTP, then type your login credentials and again try to log in from here. Yeah, WinSCP they can use if they have Mm-hmm. Yes, so working like you are not able to upload to your folder, you can like Google it WinSCP and you can download it in your Windows for Windows users. Yeah. Yeah, so I will do it here also. So you need to install it. So those who are having issues with this MOVX term for uploading, so they can install it this WinSCP and then log in using WinSCP. So everyone have got now this zip file in the portal. So we will like unzip it using the command tar minus xvf, then the file name. Okay. So now it will show you the file system like this. So if you will list the file ls, and it will show you one folder, lid driven cavity. So if you go inside the folder, you will have one more folder, that is Reynolds number RD100. Okay, so just go to this folder and you will see the OpenFOAM three folders, zero, constant and system. So everyone have got to these folders, zero, constant and system. So similar to here, we have three folders in this Reynolds number 100 case, zero, constant and system. So first we will go to the system file. If we see the folders, what files the folder contains. So in system we have multiple files. So first we will do with the block mesh file. So block mesh file is used for defining the geometry as well as the meshing part. So we will edit it using the same vi space system, then file name block dict. If you open the block mesh file, you will see first thing is the OpenFOAM header. So everyone have opened this block mesh file. खुल गया? So if you will see, there are few lines which defines the OpenFOAM logo and the full form of OpenFOAM and version information. Then form files defines the format of the file, the class and the object where it is defined. The second like after the header file, you will see scale parameter, which is usually used when we are like drawing the geometry in scaled manner. If you have a cube and its actual dimensions are 0.1 and you are making it in 10, like if it is a length of 10 and the actual dimension is 0.1, then you have to scale it like by 100 times. So this is the parameter. So here we have used 0.1 and we are actually making it in a one term. So the length of the cube, if you remember from the lid driven cavity, was 0.1 in actual space. So physical problem. So but in meshing we will use this is like the cavity. So if I draw the axis x, y and z, so this is your z direction and this is 0.1. In meshing we will make it 1 and 1. So to scale it to actual geometry we will use the parameter 0.1 scale. So in the below that you will have the vortices information. So you have to define the vortices, like this is 0 0 0. So this would be 1 0 0. This kind of things you need to define it to define the geometry where this lies. So this is x1, this is x1 y1 and this is x0 y1. Similarly this is in z, so this is x0 y0 1, or z direction we have extended it to 0.1 because we are solving for 2D case, so we need only this xy plane. And because of the inherent property of the solver we are extruding this in z direction. So that's why we can extrude it in n number of times, but for one cell we have taken 0.1 meter in z direction. So if you will see the vortices definition, you will see 8 vortices are defined, 1 2 3 4 5 6 7 8. So these defines the geometrical locations of the geometry. Then to map it you need to, like this is the geometry, then you need to discretize it in number of parts, because in the open form in the finite volume we usually solve in a discretized manner, like we have to discretize the domain in number of cells, which is known as meshing. So we need to discretize it in x direction as well as in the y direction, and in z direction we are taking only one cell, so we don't need to do the in z direction. So yeah, we are using, it's actually in actual it's 0.01 because we have scaled with parameter 0.1, so the z direction 0.1 will be scaled treated as 0.01 in physical space. So it will be like, so the coordinate 1 comma 1 comma 0.1 will represent in physical space 0.1 comma 0.1 comma 0.01. Okay. So that in the next definition of blocking, yeah, file is showing, but in the before that there is a scaling parameter, that is 0.1. So it is scaling all the dimensions. If we will make the scale 1, then it will be the actual dimensions written in the file. So definition of blocking, actually hex is the block, because we have only simple geometry, so we will make only one hexa block and we have to define this block using the vortices. Let's suppose this is 0, 1, 2, 3. I will make another one. So this is 0, 1, 2, 3, 4, 5, 6, 7. So these are the vortices of the cell or the block. So we need to put cells inside it. So we will write this command hex, and all the vortices will make one hexa. So because hexa has 8 vortices, so this is the information of vortices. Then we will put how many number of nodes, nx, ny and nz we need in our block. So if it's like x, if we suppose x, y and g, then we need to discretize it. Like if in the figure it's showing 20 nodes and 1 node. So it means this x axis is discretized in using 20 number of cells, and y is defined in 20 number of cells, and z is defined in 1 cell. So this is the number of nodes. So can you, yeah.
Is there a sequence to describe the hex code?
Yeah, if you have multi-blocking, you need to describe it accordingly, those merging pairs. But here we have only one block, so it will not affect. If you have multiple blocks, yeah.
Any sequence?
No, you have to define it like this: 0, 1, 2, 3, 4 in x plane. Then you go to next plane from origin 4, 5, 6, 7. Yeah, it's like anti-clock in the plane.
That is for phase. That is for
Yeah.
phase definition.
Yeah.
But yeah, this is for first to describe a first plane, then you
Yeah.
extend it to Z.
Z. Yeah. So then we will define the grid points. So total mass like total grid points will be, so if we see the total grid size, so it will be calculated 20 into 20 into 1, something like this. So if we want to define the grid, you can change these numbers and then you can check. So there is one more thing, is your simple grading or grading. Which is 1, 1, 1 in this case, to keep it uniform. Like grading is usually refers to how the expansion of the cells in x or y direction should be. So let's suppose if I give the parameter 1.2, so the first cell and the second cell will have the expansion ratio of 1.2. So the mass like would look like something like this. Then bigger cells, then more bigger, then more bigger. So this is grading kind of thing. So this is grading in y actually. And if you have in x also, then you need to, like in x you have grading. So this cell will get bigger. So this expands. So this grading for this case, in our problem we are using uniform grid, where each cells are of same size in x and y, which is controlled by this parameter simple grading. Okay, so the edges we don't need to look at in this case. So then we need to define how we will define the apply the boundary conditions, because here we know this is the fixed walls and this is the moving wall or moving fluid. So how the code will identify which phase is what. So to define it, we have this kind of syntax: moving wall. So moving wall is top one. So they have defined it based on it, the phase, and then fixed walls is also wall. Front and back is given as empty condition because we are solving in 2D. If you are solving in 3D, empty means there is no information in z direction. So we are assuming that in z direction it's uniform 2D cells, which is having the whole information of the x and y plane. So usually in open form, if we want to use the 2D problem, we have to give the front and back empty. So these are like z faces. Okay, so in the merge patch pair, the last thing is for multi-grid, multi-blocking, where you have multiple blocks and you have to match the pairs for the meshing. For this is not useful in this case. So now we have defined the meshing parameters in block mesh. Okay. So I will quickly go through once again. So we will open the file block mesh in the system folder, and then we will find, first thing is the OpenForm header files, which is compulsory file for OpenForm solutions. If you will remove or alter anything in this, it will not run. The OpenForm will throw error that the header did not match. Okay, so you don't need to touch this thing. Then second thing is your scaling parameter, which will scale your geometry to actual sorry, things. Then is your vorticity definition to define your geometry. Then definition of blocking, definition of edges, then your boundary names. So now, so we will see the pressure conditions. Now we will go to the boundary conditions. So we have defined the geometry, we have done the discretization of the domain. Now we have to apply the boundary conditions. So these boundary conditions are usually given in 0 folder. So we have two files, P0P, which has the pressure conditions, and 0U. So if you will see, this is the file header, which is common for all OpenFOAM files. Then comes the dimension, where the dimension is of the pressure is given as, so dimension is usually meter second, MK system is there. So yeah, so this is not meter, this is meter square per second square. So this is basically P by rho in solution algorithm. So in after dimensions we have internal field, where internal field is your initial condition. So internal field is basically the information which you are supplying to solve to the PDE. What is the initial condition? So if we are giving 0, it means each cell at initial is filled with a 0 pressure value. Then it will iterate based on the initial condition. You can define any boundary conditions for this pressure, but they will lead to different convergence rate based on your initial condition, because the initial condition is sensitive for the convergence. So next is your boundary field information, where you will define which patch have what kind of boundary conditions. So we have defined the Newman boundary conditions basically for all the walls, and front and back is empty because it is for the 2D flow. So in the pressure, similar to the pressure thing, we have the same things in the velocity. So if you will see, the dimension of the velocity is meter per second, and internal field is filled with 0 velocity in the initial, this is the initial value, and then boundary field is your boundary conditions, where moving wall has a fixed velocity of 1 meter per second, which is given in U, V and W format. Uniformly 1 meter per second is the plate velocity, and then fixed walls have no slip conditions, which ensures that flow is at rest at the walls. And the third one is the front and back, which is the empty condition for 2D flow. So transport properties, now we have defined the geometry, we have defined the mesh, we have defined the boundary conditions, initial conditions. Now what are the physical parameters which the flow is having? So these information are usually contained in constant folder. So in constant folder you have transport properties, where you will define the value of nu, which is the kinematic viscosity, which will be the driving parameter for Reynolds number, and your turbulence properties. If you are solving for RENS, you are solving for LES, or you are solving for laminar flow. So the keyword laminar represents the laminar flow, RAS represents for the RENS flow. So RAS, you have RENS models, K epsilon, K omega, whatever is there, you can use it. For this problem we will be using the laminar, because the Reynolds number is 100 and the flow is fully laminar, incompressible. So now why after physical parameters we have the control dict file, where we will control the solution algorithms, like which application we are going to use. So application represents here the solver already available in the OpenFOAM. So we can directly call them by their name. Icoform is the solver which we will be using for this problem. So we have given Icoform. Then the second is start from. So start from, sometimes what happens if we are running the problem and it is writing at particular intervals and it got some error and then it got diverged, or we killed the simulations, then we want to start it from that point. Then we need to give the latest time keyword here. So if you see start time, you either can have start time or you can have latest time. So you can use any keyword to start the flow, but latest time in that case, if there is no time directory in the folder, only 0 constant and system is there, then it will directly take to the 0 as a latest time. Okay. So even in start time, if you want to change the start time, you can define in the next way, start time 0 or non-zero, depending on your problem solution, whatever problem you have solved. So we will see it subsequently. Then stop at end time, and then end time you can define which physical time you can stop it. Delta t is a crucial parameter which will be governed by current number. So current number is basically the stability parameter. For simple case, it can be treated as physical velocity divided by numerical velocity. So from here, this is the current number which governs your time step actually. So if you mostly for numerical stability purposes, we keep this current number less than or equal to 1. So based on it, we will calculate the delta t, because in the mesh we have already fixed this delta x. So for the case of 20 by 20 by 20, we know this whole length is 0.1 meter and we have discretized it in 20 sections. So what is the output? It's like 0.005. So this is our delta x for our grid. For this case, 20 by 20 by 20 mesh, we have this kind of delta x. So we put here, and u we already know is 1 meter per second for our case, and if we calculate for current number 1, so it will look like this, then 0.00. So this delta t will come approximately at 0.005 or lower, because we have taken the current number 1, so we will put lesser than or equal to 0.005 as the delta t. So this has a very huge effect on the solution. We will see it, and when we run it, then we have write control time step. So how you want to write the data? If you want to write every 100 iterations, or you want to write at every 500 iterations, that depends on your problem. So in that case, we are writing it at 20 intervals. So purge write is like when the page completes, it will like purge out the rating data. So we have off it. Write format is ASCII format. You can write it in binary also, but that will not be handy to read. Then write precision. So after decimal, how many decimal points you want to write, and your write compression. If you want to write in compressed in form to save your space. If your mass is very large, we usually use it. And then time format is general, and time precision, how much precision of time you need in writing time is there. So second file comes with the FV schemes, which defines how the different terms in the momentum and continuity equations are discretized. So first we discretize the temporal term, which we use Euler, which is a first order term. Gradient terms are using Gauss linear. These are the iterative schemes actually. So divergence schemes are using Gauss linear also, and then Laplacian Gauss linear orthogonal. So in FV solutions, you will see basically in IFO form we are solving for pressure and velocity. So in every solution you have pressure, one condition for pressure and one definition for velocity. In pressure we are using the PCG, which Professor Day have discussed, linear solver to solve the discrete equation, and tolerance is actually because we are using the iterative solvers, so we need to set one convergence criteria. We need to tell at what type of residual it should stop the current iteration. So that is defined in its tolerance, which is basically a residual evaluated by substituting the current solution into the equation and taking the magnitude of difference between the left and right side of the equations. So whatever, like you have solved for some p and u, now you need to check if this is the correct solution or not. You will put those values in your whole equation, and then you will see the difference between the LHS and RHS. If that difference falls below this, then your time loop is completed, then it will go to the next iteration. Otherwise, it will again reiterate for pressure and velocity, and then it will solve. Additional criteria is your relative tolerance, which is your ratio of current to initial residuals. So in the first iteration, you have got some residuals for LHS and RHS, which is a basic difference. And after simulating 1000 iterations, you have got some kind of difference value. So if this value is 0, denotes you are not using this criteria and it is governed by tolerance only. If you are defining this, so either of this satisfies, it will complete the iteration for that step, and then it will go to the next time step. So here in the piezo collectors, piezo solvers algorithms, we have n outer collectors where it will momentum predictor equation again will be solved in number of loops. So this you might change to 5, and depending on the problem complexity, and then pref and the pref value can be defined, because we are using 0 initial, so we have defined it 0. So now let's start with the running one case and seeing the results. Okay, so I will also parallelly do it with you. So you need to go to your folder where you have decomposed it. So go to this 0 constant system folder. Okay. Just run block mesh command. Just type block mesh and hit enter. It will write something. Okay, so if you will scroll it, you will see that it has written something. So block mesh. So if you will see, cell size is 0.005 in I direction, it means X direction, Y direction, and Z directions. Because we have one cell only in Z, so it is 0.01 only. Okay, no merge pair are there because this is single block, and we have total number of cells 400 because we have given 20 by 20 by 1, and number of faces it has calculated as 60/40. So, and the name of the patches are moving wall, fixed walls, and front and back. So now our mesh is ready. So there are two methods in running the simulations, either in serial mode where we have less mesh size like 400 or 600, we can run it in serial only, it will not take much time. But sometimes we have a mesh in millions, so we prefer to go for the parallel mode. So first let's start with the serial mode. Just type the solver name icoform and hit enter. It should show some iterations going on. Just check if you are getting this kind of numbers. Okay, so everyone have got this. So now if you will do ls, you will see some time directories are there, right? So you need to do one thing to see, actually these are the flow fields at different time intervals. So if you want to see it, you need to download this, and then you need just type pwd, which will show you the print working directory, and copy this address. Okay, pwd is the command, print working directory. So just paste it here, or those who are using WinSCP, they can directly download using WinSCP. So just press here and enter. It will guide you to this directory. So just download whole case. Just select all folders, and here you will get the download selected files for MovaXterm. Okay, so you need to download it locally. Actually, I am downloading in desktop. You can create one folder, lab session. Okay, just download it in cavity. Whatever folder name you want to give, you can give. So it will download, start downloading. It will show something like this here. Okay, so if you are having issues and downloading, let me know. So as we are running out of time, we have to go for lunch also. So we will go for visualization. So just open ParaView. Just type ParaView in your system and it will open whatever version you have. Okay. So you have to open the file. Okay, so first just open a notepad. Not responding, क्या हो गया? So just open a notepad file, any notepad file in your system, and then save it, save as. So in the same folder where you have downloaded those case files, time directories, just go there where you have downloaded these time directories and save it as any name, para.form. So extension should be .form and first name can be any according to your convenience. You can use it para.form and change it to all types. Basically we have to create one empty file in the folder with the extension .form. Okay. So this file is to be loaded in the open ParaView. So you go to desktop where you have downloaded and you will see this file, .form file. So I will again repeat for you. Just open any notepad program in your system. Just go to file, save as, and save one file with the extension form .form. Okay, and change it to all files and then just save. So it's just a blank file. Okay, and then you need to read this file using ParaView. This blank file, open, go to this para.form and then okay. So it will show something like this. Para.form will be read here. So if you will apply, it will show you something like this. So yeah, so if we want to see the streamlines, so basically if you see the RIA problem, it is something like this. So at Reynolds number of 100 we have run, so we must get something like this contour for streamlines. So you can change the variables p to velocity if you want to read. So velocity is something like this. If you want to see the wireframe or surface with edges, you can see the mesh also. So these are the 20 cells in X, 20 cells in Y. So if you will see in Z, only one cell. So this is the domain we have created using block mesh. Okay, so if you want to see the surface, this is the surface. So if you want to like present the streamlines over it, we need to take one slice. So in the slice, this is the option of slicing. So don't worry if you are not able to follow it. Actually, we have again will do in the second session, the peer session. So you can do it there because of the time constraint. I need to. So we have Z slice and then apply. So now you will see one slice is there. Okay. So we will show plane off. So now I will put the streamlines, and the density of streamlines should be so, and it looks like this. So it is quantitatively something like this. So if you will see this image and this is something similar, or if you want to visualize it in better way, so there is one more option to surface LIC, which is line integral convolutions. So we will do it, I will show it quickly. Surface LIC loaded, slice in Z, apply, then pressure, velocity, and see. So this is something where you can see all three, this smaller one and this smaller one again and this bigger one. So this is with match with this Gia's result in 1982, which he has published. This, so for this you need, I will repeat again. So this is a paraform which we have loaded simply. Then go to slice, take one slice in Z normal and apply, you can off, and then you will go to velocity, and this there will be surface LIC. So this is actually in tools plugins. Just check if it is already loaded in your case, it might be. So you can load it from there, surface LIC. So it will show you this kind of plot. So if it is a time series, we have so we can see the time because the streamlines are not much changing. So flow is almost. So if you want to put the vectors instead of this, so let's suppose you want to see the vectors, how the vectors are showing. So you can go for GIF, and then it will show you the scale view vectors. You can scale it. you can off, you can see based on it. Okay, so you can test it for different Reynolds number by changing the transport properties. So similarly, like the Reynolds number is controlled by transport properties. So you have nu 1 e power minus 3, which makes your Reynolds number like ud by nu. So here you have 1 e power minus 3 and then u is 1, d is 0.1. So it's coming to 100. So if you will change it to e power minus 4, it will go to the 1000. So similarly, you can change the new value or u value to control your Reynolds number, and you can generate different flow characteristics and match with the Gauss result. Okay. So next two, those remaining two I will upload it on Slack. You can practice it, and if you have doubts, we can discuss it. Okay. Okay. Thank you.
Okay, good afternoon. Welcome back for the afternoon session of day 3 of NSM workshop for HPC for CFD. Professor Ashok will continue talking about compressible flows. It's a very interesting topic. I'm sure you will not feel as drowsy after the heavy lunch, and you will pay rapt attention to what Professor Ashok has to say. Thank you.
Okay. Yeah. So I'm perfectly audible, right? Okay. Good afternoon. Welcome back. Yeah. Though topic is a little tricky, so I'll put my best effort, try to or keep you wake up. But let's see how far I have been successful. So let's start with the thank you slide. I think thanks for first session, or you can interpret thanks for coming back to this session. So either way, or thanks for organizer thanking for the lunch. So whatever. So it serves multiple purposes. Oh, I am thanking because I got a chance to come here to meet my old buddies here. So that's what I am thanking. Okay, let's come to this part where, yes, let's spend a minute here, because as soon as you go to the first slide, it would be really drowsy. So idea here is that I think probably start with this drowsy slide, but I'll take up that question and start with that. I think probably the best way to go. Okay. See, one question was there in the morning session, that when I go to compressible, or I think there are two questions which are along the similar line, but eventually I look at them pretty much in the same fashion. One question, if I remember correctly, it was that if I have a compressible and I want to use that for the incompressible flow, right? So what do I do? Would that work or not? Right? That was one of the question. Another question was along the similar line, which was there in the Slack channel. If I have a pressure-based solver, can I use that for the compressible situation or not? Because we are mostly concentrating on the talking about the incompressible part, where we got, assuming here or she understood it correctly, that we decoupling the pressure and velocity. That's the idea about that incompressible solver. Okay. So let's begin or try to answer this question. Probably then the session will go nicely. If we try to answer this at the end of the session, have some understanding about this, I think then the job is done. So first question, compressible solver, if I want to use it for an incompressible region, the answer to that's very specific answer, yes. But it's like Mahabharata, yes, then I will take a pause. But dot dot dot. So these dots I am going to, or I am trying to answer that. Okay. The why these dots are there, if you use, then there would be problem of the convergence, there could be problem of the numerical instabilities. Let's take a number, then try to understand. Let's say my solver, which is developed for all compressible range, let's say Mach number higher than 1, 2, 3, it can work even 5, 6. I try to use a Reynolds number 0.01, 0.001. That's the extreme limit, or 0.001. That's the Mach number limit I'm trying to do. Theoretically, does the solver work? Still the answer is yes. Practically, gives you a hell lot of problem. It would be a nightmare to get proper convergence. Okay. Why it so? In a simple physical understanding, as soon as you go down to that level of Mach number 0001 or that low, extremely low, scaling of the acoustic scale is going to be a big problem, which is eventually one of the underlying assumption while developing this kind of compressible solver. What you see the equation system here, which we are going to talk about. Okay. So that is why if you have a compressible solver in hand and straight away go for a other extreme of the low Mach number, it's a tricky situation. You can certainly use that, but you have to do some sort of an special, or rather you need some special treatment. Special treatment in the sense preconditioning technique, if you have heard about that, you require to your governing equation. You need preconditioning to scale down the acoustic scale to that low Mach number. You do artificial compressibility kind of approach where again you scale down. So basically what you do, the compressible solver or set of governing equations that you have in the coupled fashion, so you reduce the stiffness when you go down to that extreme of the incompressible limit. So that answer my first question, and that's motivation of the second half, why we are going, or why we have segregated two sessions separately. The second question, it was is that if I have a pressure based solver, if I mean that's what typically happens in your ANSYS. ANSYS has both the option, if I can use that for compressible regime or not. Again the answer is yes. Theoretically you can do that, there is no harm in doing that, but again you have to use your judgment, understanding how much you can use or how much you cannot use to get proper or accurate results, or reasonably acceptable one. Okay. And sometimes it may so happen that the pressure based solver in a high Mach number range, it depends again. Say let's say if you try to do Mach number 0.91, probably you are good to go. It may not be a problem, and but if you go to Mach 2, Mach 3, some scales in the actual problem with the physical problem you may miss out. It may not be able to capture those shock interactions and things like that. Because what is happening in the pressure based solver, you adopt the similar kind of methodology. You decouple your velocity to pressure, solve the momentum equation, then whatever mass conservation or lack of the imbalance you have, you put it in that again, but density would be sitting there, because in your compressible case your density is now variable. So you cannot take out the density out of the loop, but density may sit there. You still get a pressure Poisson equation. Source term would look in a slightly different form, or still that source term essentially represent the mass imbalance of a particular cell. You can still solve that and get the correction and then move ahead. So there is no change in the technique, similar methodology would work. Only thing, the equations or things you have seen in the slides there, the density was not coming into the picture. Here every equation system your density would be sitting. So even when you look at the continuity equation or mass conservation equation, your rho would be sitting inside. But it's doable again with a ... that where I can use or where I cannot use. Then when you go or move to the high Mach number zone, what it does that you might not be able to, especially when you are interacting with the boundary layer with the shocks, when you have a crossing shocks, in this kind of situation probably it might not give you that accurate results as much. While if you look at the global parameter, let's see if I have a internal flows, I look at the drag, I look at some CP, you may be okay. But if you go to a more finer details where the shock is captured, how much the finer details in the sense, as soon as you go to compressible zone, then the shock interactions, cross shocks, shock boundary layer interactions and all this, what is the width of the shocks, how much it is diffused. So that makes a lot of difference. That's the finer details that I am kind of referring to. So shock should be a sharp interface, if I have to say this. Come here, let's say with any flow variable or temperature, immediately jump or pressure, it goes to the next step. So it's a very, very sharp interface, and it's a thickness is few millimeter. It's a very, that scale that you are talking about the shock capture. So one of the biggest challenge in the compressible flow, how well, how accurate, how precisely you can capture this sharp interface. So that makes different blend of compressible solver, or within the compressible solver different blend of discretization scheme, which is mostly I would say the special discretization of the convection term. Now I go little technical way. So convection term discretization is going to play a big role. So how accurate one you have, or what is the accuracy of that one, or precise, that accurate would be your shocks capturing process. Otherwise, you would be probably, so this is where if you use a pressure based solver, you would be still able to capture the shock, but it might look like a diffused. When I say diffused, what I mean that this is my straight jump and this is my shock front. When I say diffused, it might look like this. But both of them may not make a lot of difference in the global parameter. But if you go to look at the shock, this is not the actual shock I am capturing. It's more like a broadband, so diffused one. That's not expected. That's physically, I mean, it's an unphysical behavior. If I say technically, it's an unphysical behavior. So your scheme should be accurate enough to have this sharp. I mean, this is still thicker. I would say this should be like this, more straight. So that's the sharpness we are talking about that one should capture. So this is going to dictate what kind of compressible solver you have, especially in terms of convective discretization. There are plenty of out there. We'll talk about few, but give you or try to give you an idea about how they are evaluated or how they are proposed. So not, I mean, look at the equation system. It's more like when you go to compressible part, you write everything in this kind of, I would say, though I don't want to, it's a cryptic form, but it's more like in a compact notation. So it includes everything. So you see the W variable, that's your conservative variable. So rho u, rho v, everything. Then you have the, so C stands there, subscript, that's a convective terms. So which has the flow plus the pressure gradient term, if you see here. And then here, this is your viscous term, so that's why the subscript V coming in. Then it's a source term, again depending on a particular problem that you are dealing with, your source term is going to represent. So that's the whole equation system, they have been put it together. Okay. Now, what it does that, so anyway, we have talked about this, basically there are different blends of method, but yes, here I would like to make a comment, but most popular methods are obviously FVM or FDM in the compressible phenomena, which doesn't mean that spectral or FEM cannot be used, but the complexity level is much higher, okay, because already you have so much of complexity inside your flow field. So these things, I think we have done a lot of discussion. So you have structured grid, you have unstructured grid, you have now block structured grid. So another variant I have pulled in here. So block structured grid would look like this. Then you can have this kind of chimera grid, which is a very special kind of grid. It's not all solvers can handle this kind of grids. You need a very specific solver to, because there are hanging nodes. Okay, so you have to be careful about that. It's not your standard solver can capture the hanging nodes. So this is a very specific, there is one NASA solver which is openly available, they can handle the chimera grid. I think not openly available, the NASA uses that CFL3D. So that is capable of handling this kind of hanging nodes. It's not any standard solver can do that. So that's a classic definition of different kind of grid that you have. So this is the part actually I some lightly touched upon in the morning session. So you have the structured solver and the unstructured solver. So why I am bringing in here again, because these grids are there which are going to make a lot of difference. So structured solver, as I repeatedly said, it's a subset of your unstructured solver. Okay. So unstructured solver, except that hanging grid, chimera grid, you can handle any sort of grids, but the structured solver can only take care of the structured grid. Now you may ask, or which one do I prefer? Any kind of flow, whether it's a incompressible or compressible, which one is preferred? Any guess? Would be a wild guess. Anybody? Unstructured. Why not structured? What is the problem in using structured? So there is an advantage, I mean immediate advantage associated with the structured solver. The data structure handling is much way simpler. Then why would not I do that? Geometric restriction, okay. So there is one term, if you remember in the morning session, there was one term sitting there in the grid system, curvilinear. Have you heard about curvilinear grid system or generalized grid system? So I can still have my solver, which is going to behave like a structured solver. I can generate the any complicated grid, then I use the generalized system of a solver. So this is a new terminology which I have not used so far. So that means the curvilinear equation systems are, they look slightly different way. So you have to slightly derive your equation and you get back some Jacobians there, but curvilinear is another option where you can still make the use or advantage of the structural grids, but the solver is based on the system in a curvilinear grid system or generalized grid system. So it can or capable of handling that. But having said that, still the grid has to be generated in a structured fashion even in the complicated geometry. So there are softwares like Grid Pro, I think Grid Gen, which is there, Hypermesh, they can generate those kind of complicated geometry structured solvers. Nice solver. SMCFD also can do that, but that I would not say they are very good one, because any good grid generator should be solving the elliptic equation back of the mind. So which Grid Pro, Hypermesh, they do that. So they get you back the good structured mesh, then you can fit it in the structured solver, then use that. So there are ways, but let's stick to the structured and unstructured for the time being, so that would make our life little simpler. So now, having said that, that's where the structured solver becomes a subset of that, but these equation systems here, still nothing is sort of, in these steps there is nothing you need to worry about at this moment, because here it's only you are talking about the governing equations that you see. So the governing equations are written, then the different terms that you kind of handle in the compressible fashion. So there is a slightly different way you handle that, and this particular grid, I mean the particular finite element or the volume that you say, this has all 3-dimensional faces, so it could look a nice rectangular or hexahedral, or it could be a weird hexahedral, whatever you think about, but essentially you need those faces to be taken care of. And what it requires, that's here you talk about these steps. So first let's start with the transient term, that how you are handling that. So this omega is the volume of that finite cell that you bring in, then you take care of the integration. This is the, so here as soon as you see this del omega here, so that means it talks about the surface or volume. What do you think? So these are here because the whole, if you look at this equation, the answer should come out immediately. So the integration is done over that finite cell. That means this particular portion is on the volume. Then I am going down here, this term which is shown here, this is where you are bringing the surface fluxes. So the volume, so you have to use some algebra here. I would say calculus. So the divergence has to be brought in, so that the volume integral gets converted to the surface integral, and then you go about the surface, and then across the surface you get all this term. Okay, so that's how you take care. Now you can see that volume is calculated. So this is again more like in a generic fashion, so it doesn't commit about anything what kind of solver I have. So I have just a finite volume that I have in place, and how do I calculate the different properties. One of the properties is the surface areas, then the volume, and all this all these things that you calculate. Okay, and when you do this, so you may always ask this, that why are we doing this? We have a governing equations, I will integrate, go ahead with the formulation. The reason is that these things some point of time you require, so you have to store this in your data structure. So that's where the requirement of your memory and the data structure requirement goes up. So this information would be now, whether it's a structured or unstructured, some information needs to be kept. And these informations are essential because when I go to the calculation of the actual term, so there I need all this information. So you calculate all these are more like an, let's say put it a single one terminology is the geometric properties of that small cell. So these geometric properties you need to calculate a priori, and that you do. Now if I think in terms of let's say more like an implementation point of view as a programmer, once I read the grid, I will do these property calculations and store everything in a data structure. So you need to handle, so the data structure handling is always any large scale CFD code is quite high. So these things you have to keep it in the, so then you come here you try to calculate, okay, this is my particular cell and I have all these faces again which are, and across the faces I have to conserve the fluxes, so that's calculation I need to do. So obviously I need to calculate the normals and those properties which I have shown in the previous slide, that's you require those properties to calculate normals. So the normals could be outward or inward depending on that. In the surface integral, that's going to, the dot product is going to give you plus or negative sign. Then source term obviously is a volume integration, then you calculate all the flux values, and flux values you calculate the average flux values every phase. So the idea remains same if you try to make a mapping between incompressible and compressible. So the across the phases you need to calculate the fluxes. But now the flux calculations, I mean, involve some extra bit of terms which require to be evaluated, because you cannot really decouple those things from the. Now here we go into the scheme which is called the cell vertex scheme. So in the cell vertex scheme what you do, so you have a two-dimensional control volume, okay. In ij marks that particular, marking this particular control volume, and then these are the different points which are along the surface, they are sitting there. So these particular points and these particular points, and these are the control volumes are kind of encompassed with all these things, and then how do you calculate these convective fluxes and the other parameters, so that you need to calculate. Because so if you look at that in essentially the generic form, that you can calculate these average fluxes which you need in the further calculation. So here you can have another way to do that. Okay, I have an outer volume and I have an inner volume. So this is a little complicated situation, and this complicated situation would arise when you might have a grid structure like this. So these are the very specific situation which may arise depending on your geometry. It's not a very common phenomena. Okay. So but these special cases, then you need this special treatment of calculating those average fluxes. Okay. You may not need to really bother too much about this, don't get scared also, but when you have a specific situation, you need a special treatment inside your solver. Without that, you may not be able to handle that situation. That's the idea. Okay. So what important, which I started off the question trying to answer the question, that I need some sort of an different kind of scheme that I have, and what I mean that would going to give me different kind of solvers that you may have depending on the, or it may possible that a particular solver you may have all these different kind of variation. These are all can be input control, because it's only when you are programming the system that time you take care of all these different. So there could be, I mean this is primarily talking about the convection term, because the convection time is more like an, I mean that's the worrisome quantity. Especially we are talking about this kind of compressible situation where my aim is to capture those kind of sharp interfaces. I would not say shock or something, anything is the sharp interface there. So it should be able to capture that, and in order to do so, you need to have accurate precise schemes. And so there are different cadres of scheme like the central scheme, flux vector splitting, flux difference splitting, total TBD kind of scheme, fluctuation splitting. I mean, there are other also, so you can use all these different kind of ways. So what happens is that, let's say if you look at this one dimensional stencil, so simple, there is a point. The point here is that since I said that one dimensional stencil to trying to conceive the idea in a simple way. So there is an, let's assume this is a one cell, then these are I plus 1, I plus 2, these are the cell. So there is one face of this one where I am pointing out, okay, face of the control volume, this is the another face, okay. So what happens is that, so what, I mean the compressible situation, there is another physical property which would come into the picture. How is your characteristics actually propagate? Now when you go down to that situation, though Navier-Stokes equation is a, what kind of partial differential equation is Navier-Stokes equation? Anybody could tell me? It's an it's non-linear, absolutely right, but I would like to have an, it's an elliptic, hyperbolic or parabolic, what kind of PD is it? Huh? Hyperbolic, then anything else? Huh? Three options, let's take all of them, elliptical, hyperbolic, parabolic. All of them, right? Depends on the particular problem. So that's the right answer, all of them. See, if I don't have the left hand side, for example, no unsteady term, no convection term, right hand side if I do, it's an elliptical system. If I have the right hand side goes off, it's an convection and unsteady term, that's an parabolic or hyperbolic? What, parabolic or hyperbolic? Only unsteady term and the convection term, no elliptical term, no Laplacian term. Parabolic, hyperbolic. So okay, let's try to get that answer at the end. Okay. So it's the idea here is that in between you can search in Google if you get the answer. Google G knows everything. So okay. Or if I say that unsteady term, convection term and the pressure gradient term, I remove the diffusion term and the source term. So that is called Euler equation. So what kind of system is that? Parabolic or hyperbolic? That's parabolic. And when I don't have the pressure gradient, then hyperbolic. Okay. So let's get that answer towards the end. So what happens is that, especially in this compressible situation, you have characteristics, and characteristics mean the solution of that particular, the wave actually. So you are dealing with a situation where your local speed is higher than the speed of sound. So the characteristics can go in both the directions, and these directions are going to be your, so this can propagate in these two directions. Okay, one is u plus c, another is u minus c. So these characteristics one has to capture. This is a hyperbolic nature of a system. It goes in both the directions. Parabolic is one way, elliptic is also in the domain, but these characteristics are typical hyperbolic nature. So you have to capture, and all these schemes that I have, some of them listed down, to handle this kind of characteristics, and that gives you or gives rise to the different kind of schemes which can handle the shocks or the discretization of the convection term. So this is where it starts deviating, extensively deviating from your typical incompressible solver, where you can very easily decouple the pressure and velocity. Here if you try to do that, that can create trouble. Okay. So what it happens is that when you come to this kind of stencil, so that you have two faces, Even each phase you have left side, so that L and R is basically we try to represent the characteristics. So you have to represent that. So, and you can calculate in a different ways. Okay, so these things you change the particular approach, these numbers are going to change, whether the kappa, epsilon, these are going to change. But what it is, what it tells you this epsilon kappa formulation, it's more like a generic formulation. Depending on a particular value of epsilon or kappa, you can have a whole lot of different. So in one single solver that you prepare and write it in terms of epsilon kappa, something like that in a generic, and from the input control if you do, you can use different discretization as per your wish. So that's the beauty. So there is a generic way to evaluate these characteristics or the nature of these characteristics. Okay. So this gives rise to either first order scheme, second order scheme, upwind bias scheme, central scheme, but this is not all. You go to TBD scheme, they are going to be differently evaluated. So this is again the stencils which are there, I mean, okay. Now we'll just look at couple of them in a slightly details. So if you look at the central scheme, so here this is how you calculate the average flux, and then you incorporate all these parameters into it, and what you calculate, see that that's whatever inverted lambda, so that convection, that's going to take care of the characteristics of the same, but obviously they are all multiplied with the delta S. Delta is your surface area, right. So this is what is going to take care. So that V could be plus or minus depending on that the characteristics is going to be there. Now then you come to this matrix dissipation. So you, I mean, this is little messy in mathematics, I would say, but even if you don't go into that details, what it does is that I'll give you the essence of that, what it is trying to do. So when you try to discretize all these things, they are going to finally appear in this, because if you remember the first equation that we started off, your convection term has the gradient of momentum plus pressure, and then the diffusion term which has the viscous terms, which has all the shear stress and all these things. So all this you do, so you get to calculate all these parameters. So this is where things, I mean, these parameters are all thermodynamic properties of the flow. So local sound speed, you have all the gamma factor, lambda, local characteristics and the local speed and all these, because these are very, very important. You need these things when you try to devise, or rather try to incorporate in evaluating the flux. So the idea is that all these parameters that you look so messy here, so it's all you require to calculate or evaluate that flux. So my final goal is that I need to evaluate these fluxes, but I cannot do the way I have handled in the incompressible situation. So I need to have some special treatment, and these are the special treatment that I have for compressible situation, where it involves more and more calculation of more parameters, I would say. Okay. So then there is another approach called the flux vector splitting scheme. So here what you do, you have this convection flux, you have the diffusion flux. So those things you need to calculate, but the diffusion is not that much a problematic. Diffusion is always a nicely behaved quantity. It doesn't create too much of problem. Problem is the convection. Okay. So this creates a lot of problem. So one of the scheme is the Van Leer scheme. What it does is essentially it calculates these parameters. So the whole convective term that includes both your velocity component, rho u sitting there, rho u means rho u, rho v, whatever you have, all the vector quantity plus the pressure. So you need to split that both the direction, plus and minus. That's what it represents, that Fc plus, Fc minus. Okay, then what all this parameter does is simply final aim is that I need to calculate that Fc plus and Fc minus, but Fc plus, Fc minus involves lot of other parameter calculations, which is the local Mach number in both the directions, which involves, so those local Mach number also you put a check to look at whether it's in the subsonic zone or the middle range or the other range, and then calculate these things. Finally, you evaluate the Fc plus and Fc minus. So that means the whole fluxes that I have across that phase, I split it into two components in the both the directions in the along the characteristics. That's the idea, and that is why this scheme is termed as flux vector splitting. This is one of the widely used, most popular approach in compressible scenario. But then this Van Leer scheme, so there are Van Leer, Van Alveda, Quick B, and all the different kind of scheme where they get different. They get different in calculation or evaluation of these terms only, nothing else. I mean, you still evaluate Fc plus and Fc minus. How you do that are intermediate. So these are algebraic calculations, or I would say in terms of HPC, these are my floating point calculations. They are not at all worrisome quantities. How you do that? But you finally get the things splitted along the characteristics. That's what you need. So once you get that, you put it back in your Gaussian equation. Okay. So this is another one which is also quite popular, AUSM. So AUSM also different variant of families, AUSM plus, AUSM plus, AUSM plus with LDFSS. So there are different variants of schemes are there. So here again the idea is that you have this convection term. So here it shows little, I mean in a decoupled way. These are the quantities which coming from the momentum, and these quantities for the pressure, but eventually you have the complete Fc plus and Fc minus calculation. How you do that? It involves some of this algebraic or floating point calculation. These are well documented in any compressible literature or the articles. These are not a very recent method. These are methods which were evolved in 80s and 90s, but they are now well documented. You go to papers like in Journal of Computational Physics or Computer Fluids, you will get a variant of this kind of schemes on compressible flows, which are you get to see this kind of. So these are not my neither invention, or so these are well documented. So just to give you an idea, what happens is that if you only talk about the Euler scheme, so there are, you see the wide range of different kind of schemes which can be used. So there are so much of wide variation. Okay. Now which one is better than what, if you ask me, I don't have the answer. Every scheme has its own nuances. Some cases one of them works much better than the other one. But you should have one or try to use that one if you do lot of, I would say it comes with lot of experience that which one is more robust in nature. So that one probably you may stick to, but if you ask me which one to pick, I can't give you a specific answer. Everyone has his own problem, pros and cons, especially in the compressible regime. Okay, but so what you are going to kind of again get to expose is the hands-on this particular solver, which is there in open form in the density based solver called the rho central form. Okay, so this is a collocated formulation. So this is based on central upwind scheme. So it can handle your structured mesh, all polyhedra mesh, and all these things. So this solver is kind of well known for his high speed flow problem. So this is density based. So obviously, now if you try to use this, so probably when you go back home in your free time, if you have energy, enthusiasm, interest, try to do this, solve a flow around a cylinder at Reynolds number 20 using this solver. You see the problem. Probably the hands-on session you will do a problem which you will get in few seconds, that Reynolds number 20 might take a day. Still you might not get the proper answer. That's the problem. You will realize what happens when a compressible solver you take it to without, because this solver doesn't have that special treatment which I was talking at the beginning. If you go to that Mach number, you start seeing the problem immediately. And it may so happen, if you are not lucky enough, it may crash while running because of the divergence issues, the stability issues. or the stability goes down to such a low level that it will keep on running, it will never converge. But Reynolds number 20 flow around a cylinder should be a simple one. I can write a code even in any MATLAB, any environment, C, Fortran, and it should take me few seconds only. This is the difference between when you try to use a one compressible resume solver and bring down to the incompressible gem. The same thing, incompressible solver, if you try to bring down, it will show its own nature. So, ideally you should not mix match. But now even I may beg to differ also, that I would like to have a one unified solver which should work in the all resume flows. Probably that's one of the propaganda. My students are laughing at me, because I always say that I should have one which should be capable of handling my all the resume. I know theoretically in my conscience it's not possible, but that's the way you have to return it back to the students, so that get them motivated to work. But if you even get one, we have some of them in the lab, but we know the problem. That's what we are very judicious in using where we are using. Usually we try to avoid. Okay, but we have all back number resume solvers which can take care, theoretically take care, even you can get the solution, but that's what happens. Reynolds number 20 would take one day, whether I can flow over a cone and biconic cone will get in even a few hours. So, unified solver, all Mach number solvers are the nice things to have. They are well valid, but still it has its own problem. But ideally one may would like to have it. Okay. So, some important methodology, again this is what, when you go to this surface interface capturing of the shock and all these things. So, where they come, we have not even talked about where would they come. I want to capture the shock, I know the system would show some sort of a characteristic, so I will split my fluxes. I am talking about more into the convection term or convective flux, characteristics of F plus, F minus, but why do I need all this? I am listing down. Okay. So, even that interpolation of that Fc plus and Fc minus, a lot of algebraic calculations were there, which is floating point calculation. How do you evaluate across the cells? That involves some of the self quantities, right? So, if I just quickly go back, you see some of the cell quantities are involved here in these calculations. So, which means if I have a stencil, though I am trying to evaluate at the face, I have some cell center information which is required from the neighboring cells. So, how many neighboring cells I would take, what would be the interpolations, where again come down to that your FD approach kind of thing. So, these are some of the well known features or the schemes that one use for those kind of interpolations. So, these are more like an, I would say, termed as an interpolation scheme for getting those fluxes at the faces. When I take the information from the neighboring cell, the informations are sitting in the cell center, so I use that. Each of these method has different way to handle that. So, that is not the purpose of this, because that is really advanced. Okay. And also, to be very honest, I do not know very well, that is what I am avoiding. Okay. But yeah, on a lighter side, each of them, but this INNO and WINNO is quite obviously, the first one is known as muscle scheme, the abbreviation that is also used, but WINNO and INNO precisely was developed for doing that kind of interpolations and quite handy, and these are what is used. Yes, so that is the message which is scary, but that is the reality though. They are complicated but accurate. So, now it is a compromise between you want accuracy or you want easier solution. Okay, so online exam and offline exam. Online exam is always easier, you can get into anything. Offline exam is not at all a desired one. So, that is how it is. But now if you think about future and learning, you have to decide which one you prefer. So, now coming back to that particular solver, so there it uses central base scheme, that means the row central form I am talking about. So there are two different options you have. So this is based on your very famous schemes, Krugmanov-Tadmor or Krugmanov-Noel-Petrova, that KNP and KT, they are shortly, I mean if you search in Google, so based on these schemes, that row central form is developed. So you can choose that in your input file. Okay. So I don't want to go into these equations because what important here is that all the quantities here in the coupled fashion. Top of that, one thing which is missing, I realized right now, equation of state is required. Without that, this doesn't make sense. You have U, V, W, P. I have three equations. Sorry, energy is also there, temperature then. I have four equations. Then density is there. I am missing by one. So that's equation of state which is going to couple your pressure density. Okay. So that's missing. So please take a note of that. Okay. So this is how these things I know how, I mean, total energy you take into account. So the component of your kinetic energy and the internal energy, and then the stress terms and all this. So here you go when you look at a unstructured cell. This is how it looks. Though it looks nice, so every phase you need to calculate those geometric parameters. And the idea here is that you have to calculate the fluxes, then calculating the normals. Then one more important problem which would arise is the connections between this cell center P and N. So these connections are also important. How? Because what happens, just quickly give you an idea, not without going into too much of details, the connection between these cell centers are not going to align in a orthogonally. So that's going to create or bringing, this is where the challenges in unstructured solver, they are not orthogonally situated. So that means some calculation of Jacobian should appear because you have to do that properly. So these are the complexity of unstructured solver. So though it's generic one, so the solver, how it works, you start with, then you solve the, basically calculate the flux and then use that central scheme, then finally you look at the conservations. And so this is how the, in a terms of generic variable psi, so this is what I do, the volume integral to transform to the surface integral, and the surface integral you get these surface fluxes that you have to calculate. So this phi f is the variable and the psi f along the that. Similarly, the convection term would arise because all the terms are in coming from the volume integral to the surface integral, and then you need to see all this. So this is KT and KNP, how they calculate. This CA is the speed of sound, SF is the mod of the normals and all this. So at the phase, F stands for phase. So all these calculations are required, and then you look at this local speed. So in a KT it's handled in different way, KNP is handled in a different way. So finally you come down to this system which you will be solving, okay, in the gradient term, then Laplacian term, so forget about that. So what it happens that you have this density based system, so you come here, you get this momentum equation, total energy, and then solve the viscous term, and this goes in a loop and you solve that. So if you look at the structure, so obviously it doesn't look nice, so this you will again get to see. So lot of surface field has to be defined, scalar field has to be defined, so and then you calculate this. So idea here is that I need to calculate that plus and minus characteristics, so this positive and negative would come. Yeah, I think here you see, so every quantity you calculate these characteristics and these characteristics. So these are the, for the variables you do these calculations, and this is how it is defined in the variable name. And then in the input somewhere you can define what is the flux scheme that you are interested to use. So accordingly the calculation inside that would take care of that local transformation, okay. So then this is the final set of calculations, you will again see that. So the whole solver looks like that. You first solve the density, it's in a coupled fashion, nothing is there decoupled. So this is how you solve density. typical density equation. Then you assign the boundary conditions, because otherwise then you go, if it is inviscid or viscid, accordingly you solve the momentum equation, then solve the energy. If you have scalar equations after that, you can solve, that means species or something else. Then this is how it goes in. So it's everything coupled with density. That's what you finally get out the macroscopic variable out of the density, and pressure boundary conditions you also apply. Okay. So this is how that particular row central form solver works. So everything is coupled fashion, and this psi and all this terminology, you would see that how they are defined during the hands-on session, and but that's how the, but I mean it may look like an 1.c file, but there are a lot of other C files which would involve, but inherently they are doing what we have talked about in that theory. Okay. So just some of the again applications that we have been doing in our group, if I have to talk about, so this is a problem that we did for ISRO some time back in the mixings and things like that. So you see the scales, and these are all LES computation, so no steady, so all unsteady, and the computation time is quite high. Then we did, this work is also for ISRO that we did again in the mixing and trying to reduce their combustion length. So we try to look at the mixing characteristics here, the I think probably 2-3 months. So these are based on row central form solver, but obviously modified. The LES model is not the standard which is available. So right now the TA who is going to do that, he is working on non-equilibrium hypersonic flows. So it's slightly another scale. This was one of the earlier PhD student who worked on these hypersonic flows. Obviously not straightforward, that row central form that we have used, we have a different variant of that. This is which we do the multi-scaling for, or coupling with the noise, where we coupled a spectral solver for the noise and then our density based solver. Okay, so we handle this kind of sharp edges geometry again, where you can see how the interactions with the shock up with the object. So the top which you see here, there the object is stationary, the bottom case the shock is moving the object. So here you are capturing this kind of interactions with the boundary layer, that sharp edges. So we have AUSM based family here, I mean the different variant of AUSM which is quite so this is another work where we are using compressible based solver. We are looking at the Eulerian Lagrangian framework, and I mean there's some combustion problems. So okay, so this is the problem, that shock tube that you are going to do. This is one problem where it's a simple, and you can see how quickly the shock wave would generate. Then if time permits, probably they are going to run through this also, the forward step, where you can see this kind of shocks which are interacting with the bodies and all this. This is Mach 3 flow. Obviously the last on time would not permit, I know. This is again at that range where you have the interaction. So because here it would be little tricky, because you have compression corners and all these things. Okay, more and more interaction is there with the object. You have more shocks which are coming or going to feature in your physical problem. Obviously it's going to complicate the system. Okay, I think that's pretty much I have, and if you have any questions, I would be happy to take it up. So is there any question in the Slack channel, Dr. Vikas, if you can? Any question from the audience now? Yes, sir. Yeah. Come again? Yeah, I can't move, I have a restriction. So either you come little forward and be louder, then I can probably hear you.
Sir, there is one point on the slide.
Yeah.
That FEM, it is applicable over the polyhedral meshes. So can you please elaborate it more?
This one?
So the last second or third.
This one?
After that?
This one.
No. So the few points you have listed.
This.
No.
Which one?
Says the implementation of the central scheme.
Okay, okay, okay.
It went back.
This one? This one?
Yes.
Okay, okay. Yeah, so what is the question now?
So can you please elaborate more about this polyhedral meshes, how it is applicable?
Oh, polyhedral meshes, I mean in the sense I mean to say that any kind of like you have hexahedral, prism, all sort of different kind of meshes that you can handle here, because the whole solver, the row central form solver is essentially unstructured based solver. So any those grid structure that I have showed, I think I'll go back to that. Yeah. So all these grid patterns here, this nice one, this one, this one, or the kind of other one which I showed in the morning session. So all these patterns you can handle. Okay, that's what I mean by the polyhedral. So it could be any kind of surfaces that you have that can be handled, because the inherent solver is unstructured in nature. So it requires the information of the cell, it will require the information of the neighboring cell, it will have information of the vertex, it will have information of the vertex which is common to the neighboring cells, it will have the information of that surface which is common to the neighboring cell. So that all this information would be required for a particular cell to calculate its volume, normal, connections between that to the next cell, so that you calculate those fluxes properly, and whatever since they are not orthogonal or lying in a orthogonal way, so all this realignment that you need to do, so all this information coming as a geometric parameter, so that can be handled whatever the grid you feed in. So that's polyhedral in that sense. Okay, it's a different kind of grids that you generate that would be able to handle that. Yeah, any question? Yeah.
This is a question which online. The student says, consider a low Reynolds number, that is laminar flow CFD with K omega turbulence model. The solution converges but is different from laminar solution due to finite eddy viscosity. Still I am continuing. In this case, can we recognize, because we know that the solution has a laminar flow, but for complex geometries, how can we figure out whether the turbulence equations need to be used or not? Shall I repeat?
Yeah.
Shall I repeat?
So the question I understood, probably the first portion if you repeat that the.
So again I'll read it out again. Consider a low Reynolds number laminar flow CFD with K omega turbulence model. The solution converges but is different from laminar solution due to finite eddy viscosity.
Okay.
In this case, we can recognize because we know that the solution has to be a laminar profile. But for complex geometries, how can we figure out whether the turbulence equation needs to be used or not?
Okay. So there are two components to this particular questions. So obviously they are mixed up. So let me segregate the question first and then try to answer. Probably when you talk about the low Reynolds number flow, they are laminar resume flow, then you don't require turbulence model, which the student has, or the candidate has answered that himself or herself. Now when I go to the complicated geometry, that has nothing to do with the turbulence model. First of all, it depends on what is the Reynolds number that you are trying to solve, whether even a complicated geometry could be, if I try to do the pulmonary flows, it's not turbulent, it's still laminar, it's a complicated flow. So the Reynolds number is the characteristics parameter to scale down whether I need a turbulence model or not. So it is not the geometry. So that's probably the wrong concept. It's more like a flow characteristics which is characterized by the scales. That's the Reynolds number, supersonic flow Mach number, not the geometry. That doesn't dictate whether turbulence model is required or not.
I have used row central form. So in that predictor corrector approach is given, and if we remove that, so what exact difference it will make to the code?
So that predictor character step, right?
Yeah.
Now, so the which version of the row central form you are using, that makes, because if you are using the row pimple form, that would have that predictor character. Central form doesn't have the predictor character. So yeah. So that one which if you take out that you mentioned, obviously one goes in whether the solution is a Eulerian equation or the compressible equation. The other one, it will slow down the convergence. The reason why that you can say that where that character steps comes in, let me go back, then probably it will be easier. Yeah. So you are solving the density equation, then momentum equation, then energy equation. Okay. So now you have to calculate. So what you get is the rho E, rho U, rho V. So then you use the pressure to extract out the temperature. So that goes in an iterative loop. From your energy equation, you extract out that. So once you take out that, obviously that is going to have some impact, both in the solution and getting out of that variable. And without getting the temperature explicitly out, though you are solving the total energy, which is a requirement, unless you get the temperature out, the other thermodynamic parameter, which is a function of temperature, like viscosity or transport properties, viscosity, thermal conductivity, these are your strict function of your temperature and pressure. So they are going to be impacted. Automatically the overall convergence slows down. Okay?
Just to
Improve the convergence rate. So this is, you can think about in terms of improving towards the, doing some sort of an optimization and getting better solution or faster solution. Because compressible solver, whenever you try to use, and so you have a strict restriction on the time steps because of the scales that you are trying to solve. Now this row central form is implicit scheme, but you can have a row central form which can be explicit as well. So we have both, actually we use the also explicit solver. There are different reasons for that. Rather than getting into that, so I can give you some numbers which, when you use this inbuilt row central form which has the implicit time integration, let's say in some particular flow of Mach 2 or 3, if your time step, you can get a solution, convert solution order of temperature 10 to the minus 7 and things like that. Assuming some fixed grid and something. Same geometry, same conditions, if you import to that explicit solver, it would be 2 order less, minus 9. Now, why I do that or not, that's a different set of argument. Okay. There are different physical reasoning behind that. Okay. But if I stick to this particular solver, this is the time step. But now at the same time, if you look at the incompressible solver, which is pressure velocity decoupled, the solution is much, much faster. Time step requirement is not so stringent. So this is the hit you have when trying to solve compressible flows. Because you have so much of geometric parameters, and obviously these things can improve if you have a structured solver. See, every time you need to extract out those kind of geometric informations and involve geometric information, do those flux calculations, then move to the next step. It takes a lot of time. That's where it slows down. Now here if I have a structured solver, it will be much faster. That improves. But improves not by way order of magnitude, but it improves. So computing is going to be much faster. Data structure search is much faster, because when you have a typical that question that she asked, the polyhedra mesh, all this geometric information I require to involve and get the calculation of the flux and the normal and all this, then I have to search, I have to keep track of which are the neighboring cells, which vertex is connected to which neighboring cell. Even a small example of this much, I think, give you an idea. Let's say I talk about this particular vertex. So this vertex actually, let's say first I take it belongs to this cell. Now you see this vertex is common to how many other cells? 1, 2, 3, 4, 5, 6, 7. So this particular vertex is common to all of them. So I have to keep track of these cells. This connectivity is required because when I calculate this normal in this particular phase, this connectivity is important because when I calculate normal in this phase. So these takes up your time in doing this. In an unstructured solver, this is one of the inherent drawback. And especially the hit is tremendously visible in the compressible zone. You may not see this in incompressible zone, but in compressible zone, yes, surely you will get to see the impact. And that's what the typical, even a simple that kind of double edge problem, it takes few months to get a meaningful solution. Forget about a day or half day or 1 day. Nothing works like that. Okay.
One more question. In row central form, the convergence was not met when I was running. So I used to see whether solution is coming to steady or not. Same problem I faced when I used ANSYS Fluent. So there we can track the scaled residuals. So I saw that a particular pattern was coming, like the scaled residual was continuously fluctuating over the thousands or 10,000 iterations. So how to set the whether it is converged or not?
Okay, so I may not be probably able to give you an answer which is foolproof, but whatever I will try to tell you probably you will be convinced. The thing is that you are using some sort of a default parameter set which is there in the input file. That's one of the problem, is you are not getting into what it is doing, right? So there are the flux schemes, so you use something blindly. There are the interpolation scheme which you have used blindly, so which you have done same thing in the ANSYS Fluent, I assume. They are the one which is going to hit because how you are splitting the fluxes. There are a hell lot of schemes which are available. Which one is going to work for your problem? You don't know. You have picked up the one which is there in the tutorial problem probably, and that would not work a different problem. That's what you need to do or understand the mathematics little bit. That what are these flux schemes are doing, how they are actually the mathematics goes into the program, where they are applicable, where they are not, then you can choose a right one. Otherwise this problem what you are saying, these are bound to happen. I think now you are convinced. Yeah.
Sir, muscle scheme is for the compressible flow. So in order to ensure conservativeness, can we use compressible schemes such as muscle scheme for the incompressible flows?
Yes, you can do that. But then depends what kind of solver you are using for that incompressible flow. It's a coupled solver or decoupled solver. If you are a decoupled solver, you probably not required. Now, even to add to that, what kind of problem that you are going to deal with, whether laminar or turbulent. So that if you look at that muscle, what it is doing, it's just splitting the convection term in a particular way, right? So that problem even arises in my incompressible zone. So I need to have some special way to treat the convection term. And that problem would be more predominant in turbulent flows. So there you have to have some good upwind scheme. Muscle is one of the upwind schemes. So you may use that, that's not a problem. Because it's a way how you handle the convection term, right? Non-linear terms, correct. Precisely if I have to say that, it's a non-linear term. How I am handling, especially when I have a local velocity which is not going in the direction where my flow is going. It's a cell where the local flow could be in this direction. That is where this upwinding or biasness requires to get numerical stability. But at the same time, not dissipating the physics out of the system. If you have too dissipative, Always any numerical scheme is going to be stable, but then it diffuse out the things like the shock. What happens? It can happen even in the turbulence. All the turbulence would be kind of carried away if you have too much of dissipation. That's what when you are handling turbulence, why you talk about LES, DNS, you need higher order accurate system, so that you don't, because the RANS models are dissipative by nature. So it will dissipate out your system physical properties which you do not want to happen. Now, what is the purpose? If that is fulfilled, then you could obviously see even the design purposes in industry, RANS is one of the preferred model, because that gives you data in a day. But I need a design data. I am having a factor of safety to fabricate that. I don't care about the time accurate solution which academicians would like to have for writing a good journal. So there is a difference. What my objective, that should set what I want. Okay. Yeah.
This question, he says, is a general question not related to presentation. He's asking, could you please explain boundary conditions, KQR wall function, omega wall function, NUTK wall function in case of Comgast model in OpenFOAM? He has found some issues with boundary layer calculation using these wall functions. Can you answer this question?
Yeah, I'll try. May not be the best one. So the reason is that we don't use the wall functions. So that is one of the answer, probably not a good answer for him or her, because they have issues and one has to really go into the implementation what is there, because the OpenFOAM is not a black box, provided you are not using pre-installed part. Basically, if you take the source code, then you can go and look at those implementation, then see where the bug is, and it can be again problem dependent. It's not all the problem it may show up. Typically we don't use the wall function, so we try to resolve the boundary layer rather, and that's what it is. Yeah.
Anybody else has a question? Or we can take a 10-minute break before we start the hands-on.
Thank you.
Okay, so the second hands-on session today on compressible flows, again based on open form only, I'm assuming, and it will be conducted by Anurag from IIT Kanpur, who is a PhD student. Over to you, Anurag. You can have a caller mic, maybe.
Okay, good evening everyone. Today I'll be guiding you through the finite volume methods lab session 2, which will be based on compressible flows. And before beginning the flow simulations, first we'll try to understand what are the required folders that should be there in the case. Pretty much everything was covered in the first lab session itself, but I'll reiterate over here and give a recap so that you will be feeling much more familiar. So all you need to have in the case folder, any case folder, is a system folder where you will have subfiles such as control dict over here, control dict and FE schemes, FE solutions, and block mesh dict file, inside which block information and all the mesh information will be given, and that will be used to generate the mesh in our case. And a constant folder where all the properties related to the fluid and the turbulence properties will be given. And inside that constant folder also we'll have a polymesh folder where all the, as such, it's an unstructured solver as it has already been explained. So all the grid connectivity, boundary information, phases connectivity, everything will be pretty much stored over here. We don't need to touch this. It will be converted by OpenFOAM itself while we convert the block mesh dict file. And similarly, after running the case, we'll have several time directories as you might have done in simple form. So every folder will have its own variables that we are going to store. So before beginning, we will first understand what control dict really contains. So basically, we can group these entries over here based upon the time control, based upon the write control, and some other relevant entries that needs to be given to the solver. So from the, it has been already told that it's a start from entry, and you can always specify the latest time, or you can specify the start time, and it will scan for the start time in the control dict file, and it will see whether what's the scalar value that is given over here. If it is 0, it will start from 0 time itself, or you can specify any other particular time step if you have that in the folder. And similarly, we will have the stop at time, at what time we need to stop the simulation. And similarly, delta t, we'll have the delta t that needs to be given for the compressible flow solver for the initial time stepping. And after all that, we have this write control, write interval. So at what intervals we need to write, at what runtime we need to write, all those information is can be fetched from there. And in what format do we need to write the data, whether it's ASCII or binary, that can be also given. Binary has its own advantage. You can reduce the file size, but it will not be readable to us. It will be machine level language itself. And similarly, write precision, up to what accuracy we need to write the data. And similarly, if we want to reduce the further file size, we can include the write compression as well. If we switch it on, then all the folders will be in gzip format. Similarly, time format can also be given if it is general. If you want to use scientific notation, all those entries I've given in the next slide, you can refer to that. And most important thing is runtime modifiable. And suppose if you are simply running a simulation, and then if you feel like you need to tune these parameters while the simulations are going on, so you need to put this as true flag. So while simulations are running on, you can just from the other terminal itself, you can tune all the parameters like write time, write interval, end time, and all such thing. And adjustable time step, yes, we need to include the current number calculation. So based upon current number calculation, we'll get the delta t based upon the mesh size, as it has been already explained. So all those relevant entries are there in the control dict file. And each of the description I've already told you. I've given just the exhaustive list of the entries that can be given. So you can always refer to this slide, and as well as the OpenFOAM user guide as well, to get into the details, what exactly entries should be there. Similarly, we will have the FE schemes file, as it has been already told in this session that we need to discretize the convective flux very accurately as compared to the physical problem that we are solving. So based upon different terms that might appear in governing equations, like gradient scheme, divergence schemes, Laplacian schemes, temporal terms. So all those discretization schemes, mathematics are already implemented. We just need to invoke that in the FE schemes file. And most of the important thing over here is interpolation scheme. So basically, in the solver, we need to have the flux information of, variable information of rho, u, and t from the left and right of the faces. So we need to have this reconstruct rho, u, t entries over here as well, which is missing out in the incompressible flow solvers. So we will play around with this while we solve the shock tube problem. And similarly, surface normal gradient schemes are also available with us when we need to evaluate the gradient perpendicular to the face. And again, I have given the list of exhaustive files, exhaustive entries that needs to be given in the FE schemes. You can obviously, as I'm saying, you can refer to the open form manual as well. And one more word of caution over here: if you need to be very strong in the pre-processing steps. Like you have to basically, what you have to do is you have to have a good understanding whether the flow is unsteady or steady beforehand, so that it will be very helpful for us to understand what type of solver we need to employ to get the solution out of that. If we employ a different solver for, let's say, for steady state cases, and if we use unsteady solver, then we may get a junk data. Similarly, other way around, we need to be very careful for that. And of course, for surface normal gradient schemes, there will be non-orthogonality sometimes in the mesh. So we need to take for that corrections as well. So here a brief guideline is given over here on what type of orthogonality of the mesh we need to take in the corrected or uncorrected type of scheme for these SN grad scheme and Laplacian scheme as well. And similarly, interpolation schemes, we will try to see how it affects the solution. Similarly, we have the FE solution files. This is just a algebraic solver. After we discretize the equation, we need to invert the matrix, or we need to solve it iteratively. So based upon different type of algorithms, different class of algorithms are available in the open form. It's already coded inside that. We don't need to touch that. But simple few settings are already being told in the morning session itself. So for the different variables that we are solving inside the solver, if you see, we will be solving for rho, rho u, and rho e, and as well as we will be inverting the matrix of E. So all those things will be, all those variables needs to be specified over here, and the methods in which they will be inverted has to be given. And similarly, we will have in the constant folder, we will have thermophysical properties, where all the relevant properties related to the fluid, such as viscosity, molecular weight, and everything related to, such as Cp also, which might be constant or temperature dependent, will be given in the thermodynamics entry. Viscosity as well, we can give a constant viscosity or viscosity based on Sutherland's law, and everything can be found over here, and we need to fine tune it according to our type of fluid that we are dealing with. Preferably we deal with air, because air is generally we see shock waves in the air itself. And after that, we'll have turbulence properties. We are not going to look into the turbulence modeling. So for now, the simulation type is laminar, and this LES entry that has been given becomes null and nullified. So we don't need to bother much about that. And after that, now we'll try to solve a shock tube problem. So I would request you to please log into your cluster, and I'll tell you how to solve this particular shock tube problem. Okay, so we have already loaded our OpenFOAM environment in the bash RC. So if you have to look it at that again, I'm opening that file. So I think you have already done this in the morning session itself. So if you have not done it, please do it quickly. We will start the session after this. Yeah. I think everybody might have done this. So we'll start the session now. First, we need to, I've already shared a Google Drive link on the Slack channel. I have uploaded the cases over there, but we will try to incorporate the shock tube problem. So what I will do is I will type which icofoam. So I'll get to know the installation directory. So this is particularly sourcing from this particular folder. So up to here we can copy, let's say up to over here, this is the installation directory of our OpenFOAM that we have given to you. So you can always change to this directory and then see all the tutorial folders. You can see over here, tutorial folder is there. So from that, we will try to adapt our case. If you go inside the tutorials, you can see various class of problems are given over here. We are interested in compressible flows, so we will go into the compressible flow. And we can see based upon various kind of solvers, its test cases are given. So we are basically primarily interested in row central form solver. So we'll see what's there inside that. So basically we have various types of problems that we have. We have forward step case, we have shock tube, we have oblique shock, and all such viscous cases are also there, biconic 25, 55 and 35. So we can adopt according to our need and try to design our test case. So we will copy this, we will not run the solver from here, otherwise it may crash. So we will try to copy this shock tube problem from here to the home directory. So the command for which is cp minus r shock tube, and then we will copy it over here. Our code, the test case has been copied, and you simply need to type cd, and then you can see over here we have shock tube available with us from the installation directory. I hope everybody is able to do it. If not, you have to first go inside this. It's in tutorials, compressible, row central form. I hope everybody is able to do that. So if we move into the shock tip folder, you can see certain files available over here. It is 0.org. Will not be bothered about that right now. We'll have all run scripts, all clean script, and as I said, constant and system. So inside that constant, if you go, we have thermophysical and turbulence properties. I've already explained to you. You can open it and then see. So as I said, we are simulating air, so molecular weight over here is 28.96. Cp is typically 1005, enthalpy of formation sorry, we are simulating nitrogen. So we are giving HF entry for that as well. And this is inviscid case, so we are switching off the viscosity. And Prandtl number is 1 in our present simulation. And similarly, if we look into the turbulence properties, our simulation is laminar, so we don't need to specify any coefficients for turbulence modeling. And finally, if we enter the system folder, we'll have the control dict, FE scheme, FE solution. One important file that we need to have in this is we have set fields dict file. So you can see that we need to initialize the solution domain at the left and right of the diaphragm. So basically, this is a physical flow problem where one diaphragm is there, and at the left of the diaphragm we have certain state of fluid, and at the right of the diaphragm we have another state of the fluid. So we need to write a if-else kind of statement. So this set field dict is basically meant for that. So based upon the location of the diaphragm, to the location of the left of the diaphragm and right of the diaphragm, this particular values has been chosen, and this value is basically there in the literature, which has been already solved by SOD. So we'll try to simulate this problem, and we will generate the density plot out of this at 0.7 milliseconds, and then we'll try to compare our obtained results with the analytical results that is already there in the literature. So before doing that, since this is the original file, we don't need to alter this. What I will do is I simply copy this 0.org file to 0 folder. I'll put a -r over here since this is a folder. I have to copy recursively. You can see this whole file has been copied in the contents of this file. If we see the contents of this file, 0.org, PTU was there. So this PTU will also be there inside this 0 folder. So we need to have this, and we will run the utility set fields. I'm sorry, before that we need to generate the mesh. So we will do block mesh. We'll check the mesh if it is okay or not. It's saying mesh is okay, and all the mesh metrics has been printed over here. Everything seems to be okay. The number of points is 404, number of cells are 100, hexahedra cells are 100. So all those things are printed by using check mesh command. After that, we need to run set fields utility. So based upon the region that we have chosen, the region is typically from here. Diaphragm is located at x equal to 0, and the left end is situated as at -5, and the right end is situated at 5, 0. So for the solution to be initialized in region of -5 to 0, we are specifying certain conditions. So according to that, TP has been set, velocity has been set. So we are good to go with this simulation. So we will simply run row central form over here. Since this is a very small mesh, so I'm not using parallel computation for now. Our job is done. You can see I have, if you see in the control dict file, I wanted the simulation to end at 7 milliseconds. The initial time stepping was 1 e minus 6 seconds. I wanted to start it from 0 time step, and I had to write the solution at every 1 milliseconds. So this is exactly what happened right now. So you can see I started with 0, I ended at 0.007 at an interval of 0.1 milliseconds. So if we need to visualize this simulations, we need to do it in ParaView. So before that, we need to download this on our local machine. So before that I'll do pwd to know the present working directory. I'll copy this over here and then paste it. So you can see all the relevant folders that are there in the left tree, and that needs to be downloaded. So my working style is I download everything. I will leave out this 0.org and then download these files. So it will take a while. So meanwhile, what we can do is we can go to the desired location that we have downloaded. You can see a shock tube, and we can make a new file from here, which needs to be given to the para view application. Let's say this is a shock tube. So I'll name this file as shock tube, and then we'll open it. We'll not type anything over here, and then I'll simply save as all files with the extension of .foam. And you can delete this file, or if you want, you can keep that as well. We'll have to locate that .foam file. So we'll do so. It was there in the desktop. NSM, you locate according to the type of folder that you have set. So we need to open this .foam file from here. It's already there opened, and we need to click apply. So this is the problem that we have simulated right now. So you can run through this play button and see a nice animation on how the shock fronts and contact discontinuity and expansion fan is propagating. So this was done in a very fast manner. You can generate a movie out of this as well. So what we'll try to do is we will, since we have the density data available with us, I will kindly request you to download that density data from the Slack channel. I've already shared the drive link, and inside that, if you download that case folder of shock tube, I have given one folder as named as data validation. That folder should look something like this. It will have that data validation. You need to have that analytical data with us so that we can plot it. So moving on further, we have loaded the data in the paraform. This is the visual contour that we are not very much interested in. We need to have some kind of quantitative data. So for that, we have several filters available with us. We need to do a line plot. So for that, if you can see the option over here, you can apply a filter and then you can search for, or maybe you can go to alphabetical and there are n number of filters available. So we need to plot the data over a line. So I'll choose the filter plot over line. So you can see it has picked up the extreme corners, and since we want to plot it along the x direction itself, so this might not be the feasible solution. So what I will do is I'll simply click the x-axis. So this line is now passing through the geometric center of the shock tube, and if we click apply, you can see various properties are plotted against the x coordinate. These are the, if you see in this filter, these are the relevant variables that are there, and you can, we are interested to see the density data variation. So we want to select only the density. So we got the simulation results of density at 7 milliseconds, and we have data available for analytical results at 7 milliseconds. We will try to coincide our results, or maybe we will try to map the results and see how a solver is behaving. And this will be a typical test for validation of the solver. So for now, if one wants to save this data, line data, you can easily do it. You can go into the file and then click save data. So what I always do is I always maintain one separate folder for data. I create a folder over here, and let's say it's data, and I'll put the file name as data underscore the time step that I have saved. It's 7 milliseconds for now, so it's 0.007. And the easier file to save this is the comma or delimited file, that is CSV, TXT, all those kind of file extensions will be available at comma or delimited, tab delimited file. So I'll save this. It will then ask to write time steps. If you want to write unsteady data at every time steps, you can check this on. And finally, at what precision you want to write the data, you can set this. I'll keep this entries as default. I'll use the point data, not the cell-centered data. So I'll save this over here. So if you go into the system folder, you can see I have created this folder data, and at this particular time step data is available with us. You can open and then see what kind of data we have stored. So this is the temperature variable that we have stored along the x direction. Velocity, since this is one-dimensional case, so u1 and u2, that is ux and uy and uz are not required, and this comes out to be 0. So we have pressure, we have density, and we want to plot it against the point 0, that is, this is the x coordinate of that line. Similarly, point 1 is the y coordinate of that line, and point 2 is the z coordinate of the line. So this line is oriented along the x-axis. So this whole point 2 and point 1 and point 2 will be 0, and only point 0 will be changing. So we are interested to have this data plotted again in the x-axis and this data along the y-axis. So we will separate this out. We'll copy this column and put it somewhere inside this file itself. Let's say in column R. And similarly, we want to put the density data alongside it so that we can easily plot it over here. I'll rename this array as X. So we have nicely generated the data from the contour plot, and we want to see that data in paraform again, and we will try to overlap our analytical results onto that. So I'll have to make a txt file so that Paraform reads that. I'll simply copy these two columns, and then again in here itself I'll make a new text file, this data underscore 0.007. Okay, you just you can select these two windows out of this. You need to select this window where line plot is available. You go to file and then you click on save data. So earlier this data folder was not there, so you can again create another folder, let's say ABC, and inside that you always segregate this data in the different folder, because next time if you want to run the simulation it may get misplaced. So you keep it safely in separate folder and you give any name to it, and if you click OK, a pop-up menu will come where it will give the instruction whether you want to write the unsteady data at different time steps, or you want to save the single data at this particular time step only, 007, 7 milliseconds, and what precision you want to write. Filter. Okay. So you see over here, it's comma or tab delimited file. There are various options available, but I prefer comma or tab delimited. So you always choose that. So CSV, .tsv, txt, all those type of extensions are supported, and this is readable as well. You save that, and of course precision is 5 for now. You can save this. So you can see you have generated the data of the line plot. Okay, moving on further, I'll have to generate this data as a text file. I'll simply copy this, these two columns from this Excel file, and then copy it in the notepad file data007.txt. You see, our data is saved. I'll close this now. So our data is pretty much ready. All we need to do is we need to go inside, or maybe, as I said, this is the analytical result row.txt. I need to have that in the same folder as well. So I don't have right now, so I'm just downloading that file. So you can see I have two files available with me. We'll try to overlap our solution. What I'll do is I'll close everything from here. I'll delete these two visualizations as well. Or more importantly, or alternatively, you can do is close the paraview and then open it again. So first we'll need to load that two data that is available to us. Please do it very carefully this time. I'll navigate to that folder where I've saved the data. So this is our CFD result data underscore 007.txt, and row.txt, as I said, it is analytical result. And before that, if you see the row file, you see there is x comma row and several entries comma row, entry comma and then another entry is there. So the separator in this file is comma over here. So we need to specify while reading the file what is the separator available with us, so that it will try to separate out these two columns while we read it in paraview. So I am opening the analytical result first. So it's row.txt. You click on OK, and over here you can see file delimiter characters. Make sure that this is comma over here. Then only those two columns will be read, otherwise it will mess up. So click on apply. So you can see two separate columns are being generated for row and x. All we need to do is plot this data on the graph. So I'll click on the left side of the window, and you can see an option over here, split vertical axis. So basically what I'm doing is I want to see the line chart view of that data. So I'll click on line chart view, and I'm there with x and y axis. I need to switch this on, row.txt, in order to see that. So you can see some random data has been generated, but we need to plot only the density. So we'll switch off this x-axis. And on the x-axis, it is given that it is just the number of points that is there in the file. So we need to change that. Instead of using use index for x-axis, we'll untick that and choose the x array from here. You can see a nice plot has been obtained, plotted along the x direction with -5 to 5 as the shock tube length. Now what we'll need to do is we need to overlap our solution onto this file. So again, if you go into the Excel view of the data on the right hand side, you click on that, you see a faint blue colored line selection is there. Again, you need to open that data which was generated using the solver data underscore 007.txt. Now before opening that, you need to again specify the delimiter. So over here you can see there is no comma inside that. So basically it's tab delimited or space delimited. So we need to specify that in the paraview before opening that file. So I'll select that file and then click OK and make sure that you put a backspace over there and add tab field delimiter, and then you open it. You can see again that row and X has been separated out. If you don't do it, it will not give two arrays as such. All we need to do is we need to plot this data again on the same graph. So I've again selected this window and I need to switch on this data. You can see that scale has been washed out because number of points inside that is 1000. We need to scale again this based upon the X location. So we don't need this, of course, this X variable. We need to plot the density, and again we will change the index and set that as X, and we will change the color. You can click on this small circle over here. You can pick up any color you like. So you can see and you can change the name of the variable as well. I'm changing that. And you can do one more thing over here. Instead of plotting it as a line, you can put the symbols over here as well. You can set the marker style. It's none over here. You can put a cross, or maybe some other figure you would like to have. You can increase the marker size as well from this window. Now this is not advisable because there are 1000 grid points. So if you have fewer number of grid points, it would have been nice to see how this is a shock front because of little amount of mesh size. Mesh size is not tuned, and as well as due to numerical dissipation, it is not straight, it is slightly bent. So we need to make this straight. We can do from the grid tuning, we can change the schemes as well. So this is the contact discontinuity, this is the shock, and this is the expansion. Expansion seems to be pretty much in line with the analytical results. Only the sharp jumps are not able to be captured by the scheme. You can see a slight bend inside this curve. It should be captured within one grid point itself, ideally, but it is not able to do so. Yeah, it's already there. So I compared my generated results with the analytical results and tried to see how scheme is behaving. Moving further, you can save this image as well. You click on the left pane of the splitted window, and then you can go into the file, and then you can save this screenshot. So choose the relevant directory. I have saved my data in the NSM folder. So you can again generate one folder over here. Let's say it's results. Always try to separate the data and results and keep things systematic for your future reference. And then you can name this file row underscore 0.007. So you can choose the file format. TIFF is always recommended because it's giving a good resolution of the image. So click on OK. After doing that, you can increase the resolution a bit as well. Let's say 2x, and then click on OK. You will see your plot has been saved. You can open that folder. More importantly, if you want to have a different frame size, you can pull this over here. You just hover your mouse on this particular split screen and then pull this over here. You will get a nice expanded view. Again, we'll try to save it. I'll simply override that. I don't need this. It'll give you a warning and simply ignore that. Again, put a 2x resolution for this, and then save it. You can see a nice expanded view of the particular plot that we have opted. Moving on further, we'll do a small exercise over here. This is just the block mesh file. So we are putting the grid points along the edge 4, 5 and 7, 6. So for now, if you open that block mesh file, you can see we have divided the domain into 100 cells. What I want to do is you change this parameter and change it to 200 cells, and then we'll again do the same exercise and try to plot it on the analytical results, and then we'll see whether our solution has improved or not. So we'll save this file. I'm sorry, I did it in the wrong directory. Before that, we need to clean everything that we have generated in the previous simulation. So I can use the command foam clean tutorials. Then everything will be wiped out. So we need to do that process again. We'll open the block mesh file. So now I'm using 200 grid points for my simulation, or 200 cells for my simulations. So I'll do the block mesh command. Now the number of cells is now 200. And then I'll run the check mesh utility. Again, just to make sure whether my mesh is correct or not. So it's giving mesh OK. Now you are good to proceed. Again, we need to create that 0 folder. So I'm again copying that original file. It's always recommended to do in this particular fashion. Otherwise, you will have to again copy it from the system folder. from the installation directory and copy this folder, copy everything to this 0 folder. You can see again this 0 has been created. Now I'll run the command again, so row central form. This simulation has been completed. It's the end time is 0.007 seconds, and we want to extract the density from here itself. So again, I'll do a PWD and then copy it over here. So these are the new files that we have generated. Again, I'll download everything to a new folder. I apologize, I made a mistake previously. Before running that row central form command, we need to initialize the domain with the set fields. So again, I'll redo everything. Please bear with me. Our case is ready. We need to initialize the solution domain. I'll copy this .form file. Sorry. How much longer will it take? Just this is the last one. And then you copy it in the new directory, and without closing this, we will open again a new window for ParaView. We'll do the similar exercise. We'll apply the filter. You can find now this filter in the recent recent tab, and then you can click on plot over line. Again, this has pulled out the vertices only of the extreme ends of the shock tube. We need to align this along the x-axis, and then we'll click on apply. And we have generated the plot. We need to save it. Yeah, it has better, it has improved, but there are wiggles behind the shock. So that is another issue of compressible flow solvers. That is numerical dispersion. Yeah, solution may diverge sometimes also because of that. So we need to fine tune between the dissipation and dispersion inside the solver. We have various reconstruction schemes that we have, I've already told you. Yeah, like what we need to do is we have having data at the cell centers, we need to have data at the faces, like it has been already explained. So in that interpolation itself, we can add on the dissipation. So like whereas various reconstruction schemes are available in the literature, where Van Leer is one of the finest scheme, and min mode is said to be very robust and stable, but it is very dissipative. So we can invoke min mode inside this open form itself, and we can suppress that oscillations. Now, if you go back in the previous ParaView window, where we have opened our line data, again you need to click on the Excel spreadsheet view. You need to open the data over here. Remember that if you look at the file structure, this is tab delimited. So we have to select that. Add a tab delimiter, then click on apply. So where we have three data over here, we need to see this in the plot itself. So switch this data on. Again, we need to set the axis. Then we can change the color of this, let's say to maybe light green. You can see the solution has improved slightly with the increased number of grid points, but there seems to be a few oscillatory state behind this shock state. So from this, we can say that we can do one more exercise later on, and then if you have interest, you can increase the grid points further, and then you can see how solution is behaving. And if you want to improve the solution, if you want to suppress the oscillations, there are other methods as well, but due to lack of time, I couldn't cover. So maybe for the next time. And I have uploaded few of the tutorials in the, I've given the link for the tutorials in the Slack channel. You can always take a look into that. Everything pretty much remains same. I've also given you the slides. You can look into that slide and try to do your validation as well. So for now, I conclude my session. Thank you.
Guys, there's tea outside. Let's have a short break and try to come back by 5 o'clock.
Yeah.
SIDAC is the senior director there, and he's been our mentor, he's been our supporter and sponsor for this workshop. So he would like to talk to us about a little bit about parallel computing. I think a lot of you had
About architectural aspects.
Enough questions about this from the hardware perspective.
Yeah.
He will share his knowledge with us.
Yeah, thank you. All right, so this is based on some questions that were asked to me offline. So I thought that I will, in a half an hour's time, I will quickly cover how things work at the architectural level, and this is the agenda that we will look at the abstraction layers, how they are seen by the designers of the CPU, and then as applied to HPC, how do we extract parallelism. This talk is, you can say, related to what Professor Shiva covered the first day. He gave you a general overview of HPC systems, but I will just try, this is complement what he said in terms of slightly extending it down below. He started off with a 50,000 feet view. I would try to go inside the hood of the box that you normally see as a supercomputer, right? So these are the layers. So the hardware speaks to the software, or the software interacts with the hardware through something called as instruction set architecture. All of you would have heard the term instruction set, which is a collection of instructions. Has anybody of you, does anybody of you know what is assembly language programming? No? Instructions like move A comma B, you know there are registers inside the CPU, right? So, and if you want to work it at the hardware level, I mean at the lowest level that a program can run is at the assembly language, okay. So that is what separates the hardware and the software. So any program that runs on a processor talks through an interface which is called as instruction set architecture. So what is below that? I am sure all of you know that there is something called as execution units or arithmetic logic units. I am sure you would have heard about that, right? That in turn, there is something called as microarchitecture, which defines how the execution units are, how they execute. So all of these comes under the purview of, if you look at the any computer architecture book, they will talk about these things like the microarchitecture. And I am sure you know this, the operating system that runs on the hardware, and under the operating system you run an application program. So that is the overall thing. You would have seen something like a processor. On a processor the OS runs, and under the OS the application program runs. But if you really want to extract parallelism, we have to go right from the bottommost layer to the topmost layer, and that is what is shown in the next diagram. That what is that happens at the execution unit. There is first thing that happens is pipelining. I will explain each of these terms that I am describing on this slide. So there is something called as pipelining, and the next is at the microarchitecture level you have multiple execution units. So yesterday I mentioned that with reference to multi-threading. So multi-threading or hyper-threading that the word Intel uses, they introduced the word hyper-threading because there were multiple execution units, and the aim was to keep all the execution units busy all the time. That typically happens in workloads like when you have a web server. A web server is serving many clients, and each client, when it opens a HTTP connection, there is a certain set of things that particular thread has to respond to. So such kind of workloads are good for hyper-threading. And I also mentioned the other day that in whether hyper-threading is to be enabled or not enabled is done through a setting called as BIOS. Some of you may have seen that when the computer starts, there is a message ROM BIOS version so and so, it comes, and press delete to enter setup. I am sure some of you would have seen that. So that's the initial setup that one can do, and in that hyper-threading can be enabled or disabled. So in HPC systems that we use as a node, we typically don't allow hyper-threading because the entire control has to be taken by the programmer. Then in the instruction set, many of you would have heard this term SIMD. Typically computer science students they study what is called as Flyn's classification, which tells how a single CPU, single system or a multi CPU system, there is a classification for that. In that, SIMD stands for single instruction multiple data. I will explain little bit of it later. So there is an parallelism which is built inside an instruction, and those instructions are of type SIMD. I will explain more about it. That all of you must be aware of what a GPU is, heard about it. So GPU basically uses this concept to parallelize and extract more performance. Once you go up, you have the operating system is supposed to handle multiprocessor systems and multi-core systems. What are these multiprocessor and multi-core system? I will explain in the slides to come. And finally, at the application level, you are the boss. You are going to decide how you are going to parallelize your code. So all this while, I think in the last 2 days, we talked or we concentrated about the topmost layer, OpenMP, MPI. Some of you undergone course in OpenACC. They all are frameworks that are the application level. Some of them use libraries like MPI, but all of them are at that level. So I will try and make an attempt to make you understand what happens below that. Okay, so maybe you will be able to appreciate it in a better way, or sometimes some things that don't get explained in a normal way. Like Mr. Kulkarni yesterday was asking me that he was trying to scale up, and after some time it was actually counterproductive. So why does that happen? One of the possible reasons I gave him was that for the initial number of runs that he did with less number of grid points, all the data was fitting into cache. So as a result, the program was executing fast, but moment it went, the data that was being used for more number of grid points, it was not fitting in the cache. Obviously it will go in the main memory. So main memory is slower than the cache. So that could be one reason. So the reason why I am trying to explain this is, sometimes these things, if you keep at the back of your mind, maybe you will be able to explain certain observations that you see, which otherwise logically may not be explainable in a normal circumstances. So first I will explain the pipelining, concept of pipelining. So in a simple processor, the simplest thing, that the heart of the CPU is what is called as an arithmetic logic unit. So as the name suggests, it can do addition, subtraction, multiplications. These are arithmetic instructions, and there are logical instructions. Can anybody tell me any logical operator that you know of? And, or, XOR, NOT. So all Boolean arithmetic. So at the essence, the CPU, what it's doing is executing arithmetic logic instruction. So every instruction, so on one side you can treat it like a zipper or something like that. On one side the instructions are coming, and each instruction is operating on a data. That's the basic way in which any CPU works. So whether you write a program in C or any language, finally it's translated into this form. So I'm sure all of you would have heard this term machine language. So this is what happens at the machine language. So there is an instruction which consists of opcode like add, subtract, or. These are the opcodes, and it will also tell which registers to work on or which memory location to work on. So that's the stream of data that comes in. So every instruction operates on its corresponding data, which produces the results, and then the results again get stored back in the memory or register. So this is the basic way in which any processor, any computer would operate. So this is gives an example that the data that it's giving is two. So now we are talking about addition. Addition is a binary operator, so you need two operands, and those two operands are 2 plus 2, and the result that you get after execution of this instruction is 4. So that's pretty easy to understand. So now what happens in a non-pipelining architecture? So this, now you know that there is an instruction. Where does this instruction come from? It comes from the program memory. Where does the data come from? It comes from the data memory. So typically, without going into the architectural detail, assume that there is some area in the memory which is storing programs, some area which is storing data, and you are executing it. So in the previous slide I showed you that there there is an instruction that operates on the data. So what exactly happens in that is as follows. First is it goes in a cyclic manner. First is fetching the instruction, then you are decoding. Decode is what? Trying to find out what that instruction is wanting this processor to do. Is it asking it to add, subtract? So the operation to be performed is known after the instruction is decoded, because remember that these are all ones and zeros that are coming in, right? So then there is execute. Once you know, okay, I have to do addition, like then you have to add the two numbers. After the two numbers are added, we will do what is called as write back. So store the result, because the CPU has to get ready to do the next operation. So this will continue, fetch, decode, execute, write back, fetch, decode, execute, write back. This is the way in which, so some of you might have heard this term state machines that go in a cyclic manner. Even a fan is a state machine, it keeps rotating through 360 degrees. When it comes back to 0, it again rotates. That's a state machine. We see so many state machines around us. So the CPU is also a state machine which goes through a predefined cycle, and every cycle, at every stage rather, it performs certain operation. Okay. So this is what it this is what happens, that you have a instruction I1, it has to go through fetch, decode, execute and write back. Then it will complete it in 4 clock cycles. So like this, in 12 clock cycles you have executed 4 instructions, because each instruction takes 4 cycles. I think that's easy to understand. Maybe yesterday you saw the person who was serving tea, he had to go because the tea hadn't come. So I was putting in a plate the food stuff, somebody else was putting something on it, then another person was putting a spoon. So I was just passing it on. So if I were to do the same thing, all of these I would have been doing one after another, all these 4 steps, taking it from the vessel, putting it in the plate, then adding a spoon, then adding save on it. Instead of that, I was doing something, I was doing only one task, and then somebody else was doing another task. So this is called as pipelining. Okay. So that is what happens in the second example here. So now here, if you notice, without getting into details, you can see that the instruction, first instruction is exactly happening in the same manner. Sorry. If you notice here, in the fourth, you look at the in the cycle number T3, you will find that instruction 1, I think that diagram is slightly tricky, but let me explain is like this. What we are doing it is, as instead of, imagine this diagram like this, that instead of going sequentially one instruction after another, of in T1, if you look at in T1, instruction 1 is fetched. Okay. Now in T2, the fetch unit is not doing anything, right? It is the decode unit which is busy. In T3, the execute unit is busy, and in T4, the write back unit is busy. So in any cycle, only one unit is busy. So what we do is, in T2, we can fetch instruction I2. So try and see if I can collapse all of them together. Like in every fetch unit in first cycle is fetching I1, fetch unit is fetching I2 in second cycle, it is fetching I3 in the second cycle. Just try to compress them together. So what will happen is, the first instruction will still take 4 cycles, but in the T5, I2 would have completed W. In T6, I3 would have completed W. So you can imagine that happening, because we are keeping all the units busy all the time. So this is pipelining. This is available, if you have heard about the earliest processor called 8085, that onwards every processor has it. This has to be done like this, that pipelining is one of the basic features that you see in any computing, any cheapest CPU that you buy today will have this feature. So this is agnostic to the programmer, but it is happening inside. So now what is superscalar? Superscalar is, if you notice there, we have a pipeline processor, and then you have in the pipeline execution unit, you have fetch, decode and execute, right? So in the execute unit, execution is done by more than one execution unit. Why did this come? I am sure you have, yesterday it was told about Moore's law. The number of transistors are increasing, so are we getting more and more powerful system. He told, Shiva told that within 2 years you are getting double the speed, right? So why this is happening? More and more transistors are coming on the chip. If more transistors are coming in, what do you do with them? One of the examples is Pentium, wherein they made it superscalar. 80486, if you have heard about it, that was a scalar processor. That means there was only one execution unit and it was going through pipelining. However, in case of Pentium onwards, we are getting what is called as superscalar. So what are we doing here? If you notice there, if there are 2 execution unit, 2 instructions can execute in parallel, right? So your throughput becomes double, but it's not always like that. The reason being there are dependencies. If the result produced by the previous instruction is used by the next instruction, we call it as data dependency, and these 2 instructions cannot execute in parallel. The reason being, only after the first instruction finishes, only then the result has been returned to the destination register, only then we can execute the second instruction. So theoretically your performance will double, but not practically. It may become 1.2 times, 1.3 times, maybe 1.5 times, but never 2. 2 is an ideal situation. If all the stream of instructions are not dependent on anyone, if you write a program like that, your 2 instructions will executed in parallel. So that is what we see here. So here, as we see, there are 2 ALUs. So you can theoretically say that all the odd instructions are executed by one ALU and all the even instructions are executed by other ALU. However, the data dependencies should not be there. It cannot be more than, see, superscalar, this is an example. Yes, see what happens is, if you, point is that you have to look at the processor architecture, okay, as to how many execution unit it has, and you would know that. Especially if you look at the newer processors, they may have 4 units, they may have 6 units, it's possible. And more so, I mean, don't worry about the Pentium as such, but you must have heard about that there are some RISC processor, reduced instruction set processors, which are simple to implement at VLSI level. So such processors have got 4 units, 6 units, it's possible. So in which case more than 2 instructions can be executed. So that depends upon the number of execution units. And this data is not, I mean, it's available publicly, but I mean, one has to really go and dig deep into the data sheets to know about it. Alright. Now coming to the more important thing that you as a programmer can exploit, the SIMD instruction set. So now these things, they came with some versions of Pentium, and it is called as advanced vector instruction. So the way it works is as follows. The simple processor that I showed you, okay, that had got, like we say, add 2 numbers. So what are we adding? We are adding 2 numbers, they are scalar. So what is a scalar? Scalar is a single unit. What is a vector? Suppose you have a matrix which is 4 by, I mean a single dimension matrix, but there are 4 elements into it. Suppose I give you an instruction by which 4 elements in one matrix can be added to the corresponding 4 elements in another matrix, and I get another matrix by of single dimension matrix with 4 results. I hope you can imagine that. I have A1, A2, A3, A4, B1, B2, B3, B4. I add A1 to B1 to get C1. If I have to do use on a scalar processor, what I will do? I will write a for loop for I equal to 1 to 4, where I varies from and AI plus BI equal to CI. But these kind of instructions, SIMD instructions, they allow multiple data to be added to another set of data. Can you imagine this, that instead of adding just 2 numbers, I can add a set of 4 numbers correspondingly as they are present in the index, right? So this is what it does, and this is applicable to integers, this is applicable to floating point numbers. So the compiler will use the right instruction. So now where does this help us? The last point tells us that scientific simulations, AI. So wherever you are doing, wherever you are applying, what does that SIMD mean here? Single instruction. What is that instruction? Add, or the instruction is multiply or subtract, but multiple data. In the example that I gave, 4 sets of data, 4 pairs of data can be added to get 4 results. Okay, so that is what this vector instruction do. So this again our basic diagram will help us understanding what I am trying to say. You know this, that A0 plus B0 is C0, as I mentioned now. If you want to do multiple such things, you have to execute multiple instructions, right? And then you will get the 2 results, C0 and C1. How do we do, or then third one again another instruction. Whereas now imagine, see the difference, how is the data coming? As a scalar data, but in the other one it is a vector data. That means in every chunk consists of multiple data elements. So how will it look like? It will look like I take a chunk of 3 bytes, 3 source operands, another pair of 3 operands, and I directly get. So see can you notice the difference? There are 3 additions on the left hand side, and there is only one addition that is being performed by the CPU. So obviously you are going to get a 3x performance theoretically in this case, because, but remember, you have to have this kind of pattern that your data has to be next to each other. You pick up a chunk and perform the operation. Okay, so that is SIMD for you. So this is how it works inside it. So in a normal scalar processor, if you see on the left hand side, you have a 32-bit number in a register, whereas in the other case the register itself becomes 128. So how many 4 32-bit numbers can be operated upon at the same time? Okay. So now next level of parallelism comes in multi-core multiprocessor, which is handled by operating system. So you have a CPU. Now all that I explained to you is like a processor, a core, but taking the same analogy further, that you have more and more transistors, you have put more execution units, still you have left with lot of transistors. What are you doing? You are, all these features you have put in inside one core, still you are left with logic to put more and more functionality in this. So what you will do is, you will take multiple cores. Okay. So it looks like this, that you have 2 core processor or a 4 core processor. Typically in this example what we have shown is that every core has its own private cache. Okay. And yesterday in one of the lectures it was mentioned that you have multiple levels of cache. You have you are going to have some kind of cache coherency, and don't worry about that at the moment. What we are trying to show here is that in this example there is a private cache, and if you notice there is a shared cache. So yes, when you are doing OpenMP programming, these things come very much into picture, because where are you going to have that variable, whether, and compiler will manage it for you. When you say that a certain variable is private or certain variable is public, if the certain variable is public, he is definitely going to put it in L2 cache. So this is, and there are compiler flags to tell that. So that was not, I think, described in yesterday's session, because those are advanced programming practices. Typically what one should do is, first our aim should be to get the correct results, make the program functionally correct, and that may not give you the best performance. So making sure that the right data is available in the right cache, right in the sense closest to the processor which is executing those instructions, those are advanced programming practice, and maybe you will learn it later. But first aim that we should have, that we should set ourselves, is to make the program run correctly, get the right results, error should be as minimal possible, and then go in for better and better performance. So what we are showing here is a 2-core processor. A core will typically have a private cache and there will be a common cache. So in this case there is L1 and L2 cache, but in most of the processors today there is private L1 cache, private L2 cache, and a shared L3 cache. Okay. So I have, without getting into those complications, just the point that I wanted to make you aware of is, there is a concept of a private cache and there is a concept of a public cache. Public cache means, or rather than saying public, I would say shared cache, which is common to all the processors. Okay, and the reason why we put cache without going into details is because the memory that is there beyond the external bus, that is very slow, it is a dynamic memory, whereas cache memories are really fast. If the CPUs are to run at the full speed that it is intended to, then the data should be coming from the L1 cache, only then it can run fastest. And if your data can fit into L1 cache, which is, those caches are small in, I mean size is small, but still if it can fit in, then the CPU will run fastest. Anyway, for you when you are writing programs, these things are not exposed to you. You will at the most through certain compiler flags or certain reserved words that you use while writing the telling what where the variable should be, you are able to tweak it. But as I mentioned, these are advanced programming practices, maybe you will learn it through at a later date. Okay. How does now an actual node look like? A node will typically have two sockets. A server class servers typically that you get today, you can have 4, you can have 8, that is quite possible, but normally that generally we use the server class boards that will have 2 processors. So an OpenMP can run on all of them, and then you should realize that, now you will realize that there is a main memory which is common to both the processor. There is a L1 cache which is tied to every core. There is an L2 cache which is common to all cores inside a CPU. That is how the hierarchy is. The reason I am telling you is, with this you will get some better picture as to how the hierarchical memory is organized, alright. And if the data does not fit in the main memory, then it will go, as you know, to where, what is the next level of memory after main memory, does anybody know in any computing system, Linux based or Windows based? Have you heard about swap space on a hard disk? Okay, that is a virtual memory. So the program, a process or a program fits first, the OS puts it in the virtual memory, and when it is getting executed, it is brought in the main memory and then to cache and then to the CPU. Okay, so this is what a box looks like this, and many of such boxes go into a rack. Okay, so we are going to see the space-time machine of at the computer center at IIT Bombay. You will see a rack like this. Internal to the rack, you will have boxes like this. So each box is typically not, I can't tell what the architecture of Cray that you are going to see here is, but most of the clusters that you have, they will follow this method that you have a box or a node which is typically a 2 CPU system, typically, not always, it could be 4, and every CPU has got a core. I showed you 2 core. In practice, the run of the mill kind of processor that you get has at least 20 cores today, 20 or 28 cores, that kind of thing. Okay. So generally we can say that you have this kind of environment, in the sense you have multiple processors, they will have their own memory. Now again, this will be applicable to 2 types of thing. One is called as a cluster, which I will tell you later, and the one that I showed you till now. That is, you can fit both of these in this model. There we have not described what that communication network is. That communication network could be a memory, a shared memory, then we call it as symmetric multiprocessor system, or it could be a network, which I will show in the next diagram. Yesterday somebody was asking about the topologies. Okay, so Verma sir was saying that he is happy with a ring. Okay, he said that I just want a 1-dimensional array. So that is what we call it as a ring. It can be 2-dimensional like a mesh, or it can be 3-dimensional. So you see, notice the difference, what is torus. So you will find that there are rings that are made in 3 dimensions. Okay, so that is one of the architectures that is what, as I mentioned to him yesterday, CDAC is using in the network that it has designed, called as ParamNet. And these are the other topologies that one can configure. So one of the most popular one is the star, and the central circle that you see is actually a switch. So if you have 30 computers in your lab connected using, let's say, Ethernet, then all of them are following the star topology. You would see this box like this. That box up there has got a Ethernet switch, and wires, let's say there are 50 computers in this room, a wire will go to, of course here we are using wireless, but in a norm, I mean if you have in a lab where you use a wired network, the central circle in the star is actually a switch, and each of the others at the periphery, they are the actual computers, and the links that you see there are the Ethernet wires, okay? And there are other topologies which I will not get into. So finally, what is the, once we know all this, we will write an application, and when you write an application, though we don't practice it, but I would recommend that we start with a flow chart. We draw a flow chart as to what we wish to do. That's where we put the algorithm that we have in mind onto a paper. So that tells us how the flow is going to be. So these are the attributes that one should put in the algorithm that we are designing, starting with concurrency. That the whole purpose why we are here, why I am talking to you is all about parallelism. It should have concurrency. Like if you have a serial code and there are some codes which are purely serial, there is no parallelism, anything in that you can see in the algorithm. So they are not fit for parallelizing, they are not fit for the architectures that we are, the clusters that we are using like Paramutkarsh, they are of no use to be executed on that. So concurrency has to be there. Then other thing is scalability, that suppose like yesterday it was shown that beyond a point, Amdahl's law, beyond a point it does not scale. If your algorithm is like that theoretically if you can have a linear curve between scalability and number of nodes, then that is called as an embarrassingly parallel algorithm. Like any number of nodes you give, it still scales up. So that is the scalability part. Then data locality, I mentioned to you, if the data is very close to the CPU, it will execute fast. If the data is away meaning instead of L1 in L2 or in main memory or in the secondary storage on a swap, it is going to take time. And finally modularity, that is anyway, I am sure you know that any algorithm that you have, if you can break it into different modules, it is easy for you to debug and use it. Okay. So another thing is that what a concept called as accelerators. So the NVIDIA GPU that you hear about, or AMD has their own GPU or TPUs, all of them, they do what is called as they are called as accelerator. So all this while I was describing to you that how a cluster can be made, how multiple cores can be connected in parallel, but there are certain algorithms that work well on the CPUs, but now with the new concept of GPU, so GPU stands for graphic processing unit, and originally the GPUs were meant for accelerating graphics, in the sense that it displayed that characteristic that you have a display which is, let's say, 640 by 480 pixels, you can divide it into tile, and suppose you want to fill the whole screen with white color, they are independent of each other, these tiles are independent of each other. So you can assign one tile to one processing unit to fill it, another tile to another, there are no dependency between them. So there are many such algorithms or many such transformations that can be divided equally among the number of processors that you have. That is where the GPU came from, and then we had GPGPU, which were general purpose GPU, which were used for HPC loads or these days various other kinds of loads like AI, etc. So the origin of that lies in the fact that the SIMD kind of thing, that single instruction which can be applied to all such multiple data units, that is what it does. And what I am trying to say here is that there is a limit as to how many CPU cores you can have because of cache coherency and other things. So as tomorrow Bharat will tell you more about GPUs, you will realize that these cores are lightweight in nature, they are not as powerful as a CPU, but they are thousands of them, and there is a mechanism by which you can use it that you will learn tomorrow. So the point I was trying to make here is that you have architectures like GPU, then FPGAs, don't get into that, I will just mention it for your reference, it is beyond the scope of explaining to you. And there are as you know that for AI you need tensor processors, so you have TPUs also. So the aim is that specific workloads, AI related or some specific workloads, even some of the HPC workloads, people are like Professor Verma mentioned, they have ported their code onto GPUs. So what they have done is whatever are the good characteristics of GPU, whatever good GPU is doing at, you exploit that through this mechanism. Okay, so that is what the accelerated computing is. So to sum up, what you do is when you write a parallel code, you distribute the data to memories, distribute code to the processor, you organize the workflow and try to have some efficiency in that. First try to get it working correctly and then try to accelerate it. So in the last section, you already know this, that OpenMP, MPI, and some of you have used OpenACC. So this is, if you remember, the top thing that I said, the parallel programming frameworks where the parallelism is to be imparted by the programmer. The other ones, that superscalar, pipelining, that is all taken care by hardware. Some things are taken care by the compiler, but these things as a programmer you have to incorporate it. Okay. And finally, since you are all using Paramutkarsh, I just wanted to tell you what its architecture. It's a generalized one, so I will quickly go through it. I have already overrun my time, but now you would know, you are in the rack, you have multiple compute nodes, that I am sure by now you have guessed. So to connect them you need a switching fabric, plus on the hard disk side, like you must have heard about NFS, which is a network file system. So that is not a parallel file system. Imagine the same thing, but imagine that multiple programs or multiple processors are running on multiple compute nodes. Each one of them is writing to a part of the file. Normally you can open a file, multiple processes can open them in read mode, but when the OS will not allow you to open multiple processes to open a single file in write mode, because then there will be conflict as to which program writes where and all. But parallel file system allows that. The programmer has to make sure that no two programs are writing onto the same part. Reading anyway is not an issue. So anyway, I am not getting into how that works, but imagine that parallel data streams are going from multiple compute nodes to the same file. Then you have accelerated nodes, that's with GPUs. Similarly, you have some storage acceleration. I am sure you would have heard about SSDs. They are faster than the magnetic tapes. So the storage acceleration nodes, they contain the SSDs. So frequently needed code and data by the compute nodes, it can get it from the SS storage accelerator. And then you have a tape library. Now to manage this whole thing from the system administrator's perspective, we have boot servers. So these nodes, they will not boot from the local hard disk, but they will boot from the network. And which node should use what image of the OS, that is decided by the system administrator. Similarly, there is another network, if you see the blue one, which is what is called as a management network. I will not get into those details, but over Ethernet you can, now you cannot have, if you have 100 nodes, you cannot have 100 displays and 100 mouse and 100 keyboards. All that is done from the management node. Then you have, this is what you are sitting and using from the local network. So you log in into, land up on the login nodes, and from the login nodes you would be firing the job through a SBatch onto the compute nodes. That's how you use Paramutkarsh. And again, I will not go into this details, but if you notice here, there is a operating system which is a lightweight OS. Then there are some middlewares which does assignment of jobs to the nodes, etc. Then you have not the normal compilers, but you have the parallel compilers. Similarly, you have the parallel file systems. So all of this stack becomes very complex for a HPC system when you compare it with a normal computer like the one that I showed in the first slide. You have just a processor and OS and just one application running. Alright. So in summary, you have parallelism at every level, starting from the hardware to the middleware to the OS to the user, and you can have some sort of parallelism which is given by the instruction set architecture. The compiler takes care of it. Above that, you as a user have to do it, and finally you have to think parallel. That is the main thing when you are designing the algorithm, because inherently we are designed to think serially, as a human being. But then when you can think parallel, you can incorporate that parallelism, and that's all. This is my email address which you can note down if you wish to communicate with me later. So that was, I tried to like, it was like in a short while I tried to squeeze in too many things. In case you want any details on any of those, I am available today, tomorrow during dinner and all. So do let me know, and I can if you have any questions, quick questions, I can take it now. I know it's a fag end of the day. Anyway, you have time tomorrow. Today. Okay? Yeah. Yeah, we have one more.
We have a very short, quick session by a guest, Dr. who's from a company named Sanka Sutra.